Welcome to Hot Chips 31. Tutorial 1. Acceleration in the cloud.
Good morning, everybody. I'm Christos Kozyrakis. I'm one of the two co-chairs of the program committee for Hot Chips. And I want to welcome you all to the morning tutorials. We have a really great set of tutorials this morning to explore how acceleration works in the cloud, how the hardware software technologies that the main cloud providers deploy works together well. And we're going to explore issues ranging from accelerating and offloading very basic virtualization functions all the way to how to make faster the coolest applications these days, machine learning. So we're going to dive straight into this. The first speaker is Anthony Liguori, who is a senior principal engineer at Amazon AWS. He's responsible for the Nitro project, which is one of the coolest projects in this area these days. Before Amazon, he had a long distinguished career at IBM. Anthony? Great.
Thanks, Christos. All right, today we're going to talk about the Nitro project. And the Nitro project represents a journey that we've been taking at Amazon in AWS to completely reinvent the way that EC2 works. And we're going to go through the evolution. We're going to talk a lot about the role that hardware and software has played in that evolution. We're going to talk, if we have time, we're going to go deeper into one aspect of the system called the Nitro security chip, and then we're going to talk a little bit about some of the forward-looking things that we're doing in this space. To start off with, how many folks in the audience are familiar with EC2? Okay, so there are some folks that aren't. So EC2 is our cloud. EC2 is the infrastructure within AWS that hosts virtual machines that literally every other piece of infrastructure in AWS is built on top of. So when we talk about the scale of AWS, we have over 60 availability zones, which effectively are clusters of data centers that are physically isolated from each other. And each of those availability zones can have over 100,000 servers in them. So you can imagine the overall scale of AWS worldwide is in the millions of servers. And all of those servers ultimately are EC2 servers. And then they run higher level services on them like RDS, which is a relational database service, or EMR, which is a MapReduce service. Any of those services generally are built on top of EC2. So EC2 launched in 2016. And right around the 10-year mark or so of EC2, we started really asking ourselves, we have this really large fleet, we have this large business, but we're still generally using commodity hardware. We're using hardware that looks very similar to what you would buy from, say, a Dell or an HP type vendor. And if we took all the things that we've learned about operating at scale and we said, we just want to completely redefine the platform, rethink all old assumptions, what would we build and what would we end up with? And that's what really started this journey. And we'll talk more about where we landed in that journey. So that led to a system that we call Nitro. Nitro is a combination of hardware, server hardware, accelerators, and system software. So it's the full end-to-end system. We launched it publicly in November of 2017. This was with the C5 instance type, which we'll talk about in a bit. In its current form, it really got started in 2013. Although we had done some earlier development before then. And this new Nitro platform is now the way that we're building all of our instance types. So everything new that has been launched since 2017 in EC2 is built on this Nitro system. It's not like kind of a fringe project. It is literally the thing that is powering everything that we do. And fundamentally, it is purpose-built hardware and software combined together, including a brand new hypervisor. So the text is a little small, I apologize, but I'll walk you all through it. To really understand what you need from a virtualization platform, I think it's important to start with how virtualization works, right? I know there's a lot of folks in the room that have a really deep hardware background, but the specific details here I think are really important. So at a very high level, the way you could virtualize any processor is by simply taking an operating system, the actual instructions that compose of the operating system, and then trying to run it in an unprivileged mode. And so specifically, the code that is up on the screen that's a little small is the entry point for the Xen hypervisor. It's a multi-boot module. So you might recognize what's happening in those first handful of assembly instructions. So I wanted to start with a thought exercise. What would happen if we took the actual Xen hypervisor and we just ran it in ring 3 on an x86 processor? So to start with, because this is multi-boot, you can be in 64-bit mode and all that goodness, so let's ignore the legacy kind of aspects of x86 boot. But you start executing instructions, and the first instruction's a jump, so obviously you can do a jump in user mode, that's not a problem. Again, you hit just normal instructions that there's really no issue. You're doing adds, you're doing moves, you're doing things of that nature. Until you hit an STI. This is an instruction that manipulates the status of the interrupt flag. And this is a privileged instruction. And so on x86, this will generate a fault. Now, the sort of very high-level theory of virtualization is basically that when you encounter an instruction that faults, you pause, and then you emulate the contents of that instruction by something called a VMM. Now, the theory behind virtualization goes back to the 70s with a paper written by Polpek and Goldberg. And the terminology, I think, is really important, and a lot of people kind of throw around sort of terminology related to hypervisors without being very specific. But in this case, really easy. You emulate the STI instruction and you move on. It turns out that emulating that instruction, there's really only one way to do it right. There's a specific behavior that that instruction contains, and all you really want to do is manipulate some shadow register state and move forward. There's not really a lot of room for being inventive there. So once you've done that shadow state manipulation, you can just keep on moving, and again, you start executing normal instructions. And really, what's happening here is that the VMM really forms the heart of the hypervisor. It's the thing that is actually emulating in that trap and emulation setting. And in that original Popek and Goldberg paper, one of the requirements it stated was that as long as the statistical majority of instructions were running natively, you were virtualizing and you weren't emulating. And that's really the key, is this notion of a statistical majority. Now, it turns out that not all instructions can be handled by a VMM. So the next instruction in this instruction stream is an in instruction. This is a legacy I/O port access within the x86. x86 is a little unique in that it has a separate I/O address space that goes back to the good old days of ISA and things like that. Now, when you're accessing I/O, I/O is not like the STI instruction, right? In this case, I think it's the F port. But if you're doing disk access or you're doing network access, there's all sorts of different storage devices, there's all sorts of different network devices. There's a lot of personality in this. And so there's another mechanism that's used to implement these types of instructions, and that's something that's generally called a device model. And so in a modern hypervisor, what you'll see is you'll have this core VMM, and honestly, all of the VMMs largely look the same. If you've worked on one, they all kind of do exactly the same thing. But the personality of a hypervisor really is in the device models. That's where you see a lot of differences between how these different hypervisors work. So a hypervisor consists of a virtual machine monitor, many device models. So in the very least, you've got tens of device models, and something like Nitro we have on the order of 10. If you look at something like QEMU and KVM, which is a popular open source device model, it has hundreds, if not 1,000 device models at this point. Then you also have the traditional components of an operating system, a scheduler, a memory manager, and all of that kind of stuff. And as I mentioned earlier, what I'm describing to you, and which was the way that EC2 worked up until about 2013, this is state of the art since 1974. Not a lot had changed in the industry. Even though virtualization became popular, cloud became popular, we were still doing things the same way that it was done back on the mainframes. In fact, before Amazon, I worked at IBM, and I worked with the mainframe team, and they always used to tease us that they had done everything we were doing 20 years ago. So that's the way the world worked before Nitro. What's happened in this time frame? Well, it turns out Intel processors don't allow for trap and emulate style virtualization. There's a series of instructions that just don't trap when they should. So that's one problem. It turns out Intel fixed this problem by introducing a hardware virtualization mode. But then the next, sort of independent to that, the Zen open source project came up with a clever way around that original problem. And that was to introduce this notion of power virtualization. And so instead of trying to trap instructions that don't trap, you modify the actual operating system to make what are called hypercalls. So this is communications back with the hypervisor. And that's how EC2 launched. It launched using Zen power virtualization and then ultimately adopted the Intel virtualization technology to be able to run unmodified guests. This says evolution of the Nitro system. This is LibreOffice's fault. So everything I've described, this was the CR1 instance type. So in EC2, we name our instances based on their shape. So CR1 at the time, this is 2013, was a high performance instance type. It supported, CR1 I think was it might have started out as an Nehalem processor. It had 10 gigabit networking that was relatively new for us at the time at least. And this shows what the general software and hardware architecture looked like. You had just a standard NIC, standard processor, standard storage controller that sat in front of SATA hard drives at the time. And the software stack looks exactly the way that most hypervisor software stacks look like today. You have some kind of management partition. In this case, it was Amazon Linux. It's running software device models. You have a hypervisor, in this case, the Zen hypervisor. And then the actual guest, the thing that we offer to customers, sees a virtualized storage and a virtualized network model that's presented by software. There's a lot of work that goes into making this type of model performant and consistent. Looking back, I think we did a really good job, but it pales in comparison to what we have today. So let's look at the first kind of step in the evolution of the Nitro architecture that came from the C3 instance type. So this was launched about a year later. And this is the first instance that we had to introduce an accelerator. And I think in this particular instance type, I think we'd all agree that what we're doing is we're using an accelerator. So if I had this server and I put it in front of you today, it would look very much like a normal Dell server. If you opened it up, the motherboard would look exactly like what you would expect it to. But it had an additional PCI card in it. It had what we typically call today a smart NIC. And this was a MIPS-based processor. It was an off-the-shelf system. I'm sure if you know the space, you can guess what the vendor was. And we used it as a bump in the wire. So we had the PCI card in there, and there was literally a DAC in the front of the box that connected an Intel IXGB network adapter into this offload card. And then the offload card was connected up to the top of rack switch. So this model was a huge improvement for us. It was a really early stepping stone, and it allowed us to introduce a capability called enhanced networking. So I guess the first observation about introducing acceleration in an architecture like this is that it is not sufficient to just introduce hardware and then lift and shift your existing system software stack onto that hardware. We haven't really talked about it in the past, but earlier in the 2012 or so, we actually tried to do that. We tried to take just standard Linux with IP tables and this exact same framework that we were using for networking, and we tried to put it on these MIPS cores, and it was terrible. It did not perform at all. We didn't get what we wanted out of it, and we had to completely abandon that. And instead, we had to develop a new software stack that was purpose-built to only do what we needed it to do and to make use of the hardware and all the capabilities of the hardware. So this was the early learning for us about how to build a system like Nitro. You gain a lot using a general purpose operating system. It gives you a lot of flexibility. If you take something like IP tables, which is the Linux firewalling and just general traffic shaping infrastructure, it's pretty easy to compose that to do all sorts of things. You can do all sorts of SDN tunneling, you can do traffic shaping, but with EC2, we do networking a very specific way, and we don't actually gain a lot from all of that flexibility. And so where we got the benefits in the C3 instance type with enhanced networking was not just introducing accelerated hardware, but rebuilding our software stack to take advantage of that hardware. What we actually saw in this instance was an order of magnitude improvement in packet rate. So we went from about 100,000 packets per second to about 1 million packets per second, but also a 2 order of magnitude reduction in tail latency. And that was the one that was actually the most important for us, because what we found from operating EC2 for all of these years is that customers, not all customers, but there's a good number of customers that are very, very sensitive to performance variability. So what you really want if you're building a distributed system is you want every single node in that distributed system to behave exactly the same way. Otherwise, rationalizing about how the system is behaving is extremely difficult. So building upon the success of C3, we said, hey, can we introduce some more hardware acceleration? And that led to the C4 instance type. And this is around January of 2015. Now, there's a couple things that we did here that were different. So the first is that we stopped using an off-the-shelf SmartNIC, and we started working with a company called Annapurna Labs, which was a startup that was building a custom ARM SoC. And so this platform actually uses the Annapurna Labs-based card. And that specific SoC was an A15, so it's a 32-bit ARM processor. But what was special about the processor is that it had a really strong network device that was very programmable. And then it also had the ability to do a lot of interesting PCI virtualization. And so what we were able to do on this platform is we were able to first, so we continued with the bump-in-the-wire networking, but we introduced storage virtualization. And so the single card now does bump-in-the-wire networking, but then it also presented an NVMe device directly to our management partition that was a remote block device. So today, NVMe over Fabrics is pretty popular. There's a lot of startups around with various forms of NVMe over Fabrics. But we introduced this in production in January of 2015, and we've been doing it ever since. At the time, NVMe was not very mature in terms of a driver ecosystem. So we still presented a paravirtual device on top of this NVMe device, but we offloaded the actual storage data plane. Now, one of the important wins for us in this platform, beyond just improving the reliability and reducing the variability of network attached storage, was we actually were able to make more x86 cores available to customer instances. So in the previous generation instance type in C3, we were actually holding back 20% of the cores on the platform in order to do all of the device models and software. What the Annapurna card allowed us to do in C4 was actually reduce that to 10%, which is very significant because ultimately customers are limited by the size of the VM that they can get. And so if you can give a slightly larger VM, it allows them to do new and interesting things. We liked Annapurna so much that they actually joined AWS, and they were acquired, I think, shortly after we launched this platform. And that's when we started actually working with them to build truly custom silicon. And this led to the i3 platform. And the i3 platform used the next generation of Annapurna technology. And this is the one that was actually built while they were part of AWS. And so we were deeply involved in all of the design for it. And so in addition to improving the performance, so this generation of hardware was based on an A57. And again, we made improvements in the networking path and in the storage path. The other thing to call out on this platform is something that's super critical in the cloud is encryption, right? We want to make sure that every byte of data that's stored is encrypted, and that whenever you're transferring data over the wire, it can be encrypted. This platform enabled us to drive encryption of remote block storage at line rate. And so there's no penalty for turning on encryption on this platform. The other thing we introduced, and sort of our next big observation, was instead of just having a single card that tried to do everything, could we introduce multiple cards in order to change the amount of I/O performance available on the platform? And so i3 is a high storage platform. It has 8 NVMe drives. It's capable of doing 16 gigabytes per second of local storage, which is a tremendous, even today, with this platform being almost 3 years old, or actually almost 4 years, yeah, almost 3 years old. That's still 16 gigabytes of storage is a tremendous amount of storage for a single system to have. And this actually works by having 4 separate Nitro cards that sit in front of NVMe, 2 NVMe drives. So if you were looking at the topology of the system, you would see these 4 individual controllers with 2 drives behind them. And the role and responsibility of each of those controllers is to virtualize the drive that sits beneath them. So we want to present storage to customers using PCI pass-through. We want to make that hardware directly accessible. When you look at something like NVMe, NVMe is incredibly latency sensitive. You do everything you can to get out of the way when it comes to latency with NVMe. And going through software virtualization, you're going to lose a lot of the benefits of the underlying NVMe technology. So these controllers allow us to do PCI pass-through of the NVMe drives that are behind them, but also allow us to do things like normalize performance so that we can use multiple vendors of drives. It allows us to do transparent encryption so that all that data can be encrypted at rest without the customer having to do anything. And it allows us to provide a safe interface in front of the drive so that we don't have to worry about things like firmware updates. And we can do managing of these underlying drives. So at this point, we've offloaded remote storage, we've offloaded networking, and we've offloaded, there's another thing I didn't call out here that's really important. This generation of card also allowed us to introduce our own network device interface. So this is the platform where we launched ENA, the Elastic Network Adapter. And so before we were doing the external bump in the wire, and that cable disappeared in this platform. So one of the painful things about the bump in the wire model is that as you improve underlying networking technology, you have to change the way the customer sees that network. So just in the last 10 years, we've gone from 1 gigabit to 10 gigabit to 25 gigabit, and then recently we've launched 100 gigabit. And with all of those generational changes in networking technology, the thing that's important for us is we don't want customers to have to rebuild their images to be able to take advantage of those technologies. And ENA gives us a stable and consistent interface that is high performance, but also avoids having to change drivers between network technology changes. So again, we've offloaded local storage, we've offloaded remote storage, we've offloaded networking. What comes next? So C5, this is the platform we launched in November of 2017. This is the culmination of kind of this project. And what we've decided is that, well, that management domain, that the Amazon Linux that was in the previous pictures, it's not really doing all that much anymore. It's not doing any device models. It's doing like legacy I/O models, but they're not really that complicated. It's not doing any I/O virtualization anymore, for sure. It's really just acting as a control plane. It's allowing us to do software updates, to collect logs, and things like that. But there's no reason why we can't do that same work on the ARM cores that are already present on the Nitro card. And so with C5, we went all in with bringing all of that data plane and control plane onto these Nitro cards. And we were able to, and after you do all of that, the next question you ask yourself is, okay, do I still need the same hypervisor? The only thing my hypervisor needs to do now is what we previously showed as the VMM. It just needs to trap instructions. In the case of Intel, you just use the Intel VT, and there's actually not a whole lot that you have to do beyond that. A lot of our instance types, we have dedicated cores for every customer. And so even from a scheduling perspective, you don't really need all that much from scheduling anymore either. And so we also introduced the Nitro hypervisor with C5, which is a very, very lightweight hypervisor that really is just responsible for dividing memory and dividing cores among guests. So at a really high level, where we landed with Nitro really can be described in 3 parts. So the Nitro cards, which we've talked a bunch about so far. The Nitro security chip, which we haven't talked about. And then the Nitro hypervisor. So once you've reduced the hypervisor to be this really minimum footprint that's just doing static partitioning, an interesting question you can ask yourself is, do I even really need a hypervisor anymore? If all of my I/O virtualization is presented through these Nitro cards, and you just see the right devices on the PCI bus, what is the thing that is actually preventing you from just allowing bare metal access to the underlying processors? The answer is today, if you did that and you weren't careful, there's a lot of non-volatile flash that the x86 has direct access to, and you need to do something about that. And so we introduced the Nitro security chip, which I'll talk more about in a bit, that mediates access to all of that, allowing us to safely offer bare metal instances. And we talked a bit about the Nitro hypervisor already. I'm going to go really quickly through this just in the interest of time. So there's actually 4 types of Nitro cards. There's the networking card. There is the EBS card, the remote storage card, the local storage card, and then the system controller. So the VPC card. VPC is our virtual networking construct. We mentioned that this contains the ENA controller. So this is our networking driver. This driver is supported in all major operating systems today. It's independent of the underlying fabric. If you had one of these Nitro cards for VPC, and you put it into a typical server, you would see an ENA device. Like this is truly a network card. It feels like a network card, but then it does a bunch of special stuff on the back end. In addition to just presenting the ENA device, it takes care of our SDN encapsulation, implementing our firewall rules, which we call security groups, implementing performance limiters, and implementing routing policies. We talked about up to the 3rd generation of Nitro card. Our 4th generation of Nitro card for VPC, which we've recently launched with C5N, is actually capable of 100 gigabits bidirectional. So we've moved to a 100 gigabit fabric under the covers. And we also recently announced that we're able to do transparently AES 256 encryption on all of that traffic. And this is really a great example where there's no way we could offer this with just pure software on general purpose CPU cores. To be able to do 100 gigabits with high packet rates and with transparent encryption, you need to have purpose-built hardware, but you also need to have purpose-built software to take advantage of it. As I mentioned, the Nitro card for EBS presents a standard NVMe controller, and today with the C5 instance and everything after that, what you'll see in your instance is actually an NVMe device. But what's happening on the back end is that all of this is going over Ethernet today, and it goes to a large storage system on the back end. Again, encryption super important, and this is another place where like hardware was critical to enable transparent encryption support. We mentioned the Nitro card for instance storage and the capabilities on the i3 platform. The other thing I'll mention that's another critical part of EC2 is hardware monitoring is absolutely crucial for our customers. And one of the downsides of doing device pass-through versus some form of virtualization layer is you lose some of the ability to do drive monitoring. For instance, flash devices wear, they have a lifetime, and the behavior of an FTL, once you get past the predicted lifetime, at least our experience has been it's very, very, very variable. Sometimes you get catastrophic performance degradation, sometimes the device just stops, sometimes it starts to fail gracefully. You have to actively monitor for wear, and then you have to make sure to replace the hardware when you're getting into bad wear states. And so there's a fundamental conflict between doing direct device pass-through and also offering the kind of hardware monitoring that you really need to do to allow customers not to have to worry about these things and do it all themselves. So the Nitro card controller is probably the part of the system that is both the least obvious, but also the most important. So once you have a collection of accelerators in a platform, a collection of these Nitro cards, the system stops looking like a single server and starts looking like a distributed system. All of these cards are connected to each other through commodity Ethernet. And internally, it is a full network and a full distributed system where independent components can fail. You have to create quorum for certain types of behaviors. And the Nitro card controller is the thing that takes care of all of this and orchestrates the entire system overall. Very importantly, it also is the thing that establishes the hardware root of trust. So when we approached Nitro, we didn't want to limit ourselves to just increasing performance and improving variability. We also wanted to make sure that we had the most secure platform we could possibly build. And having a strong root of trust that is rooted in hardware that we build ourselves, that's running software that we 100% build ourselves, is critical to being able to really stand behind your root of trust. In addition to the Nitro cards, I mentioned the Nitro security chip briefly, and I want to talk a little bit more about how that works. So the Nitro security chip is a custom microcontroller that sits on all of our motherboards. It is controllable directly from the Nitro controller card. So there's a private interface between this chip and the Nitro controller card. And the most important thing that it does is it holds the system in reset. The x86 component of the system's in reset until the card is able to come up and measure the system. there's a whole lot of technology built around trying to protect from bias-based rootkits and things like that. We'll go through that pretty quickly, but generally speaking, I don't like most of it. Because when you have software that has to try to figure out whether or not it's running in a tainted state, it's very hard to convince yourself that, that you can prove that you're not in a tainted state. Being able to just physically hold the processor that you don't trust and reset, measure all of the flash associated with the system, and only release the x86 processor when you're sure that the system is in a known state, provides a very simple and much easier to rationalize root of trust that you can then base the rest of the system on. I mentioned I don't like the current models. We won't spend a lot of time on this, but the basic gist of these slides is UEFI Secure Boot is kind of the gold standard way of doing this on a traditional system. And it starts with the system in a very untrusted state. It executes a small bit of code to try to enter into a trusted state. But ultimately, you end up with just millions and millions of lines of code that need to be executed. And it's all relying on, OK, I'm doing the right thing, check the signature of the next thing. I'm doing the right thing, check the signature of the next thing. I've been doing software for a really long time, and one of the things I've just become convinced of is that there's no way if you've got 10 million lines of code that you don't have bugs. It's just not possible. Unless you're doing formal verification, which is not what's happening here, there's going to be bugs, and often those bugs can then become security bugs. So it's very hard for me to trust complex systems when it comes to security. Instead, we take a much simpler approach. The instance, whether it's a bare metal instance or it's the Nitro hypervisor, if it tries to talk to any of the non-volatile components on the motherboard, that's all intermediated through the Nitro security chip. And when we're running untrusted code on the x86 processor, we just stop writes. It's basically so this chip sits on the SPI bus. It sits on a few other of the local buses, and it just blocks the writes. And so it's a lot easier to get your head around why that works and how that keeps the system in a secure state. So I mentioned that by offloading all of the I/O virtualization, we're able to create a hypervisor that is much more simple, much more easy to use. And that's the Nitro hypervisor. Now, it is KVM-based, but it doesn't look like any kind of Linux-based hypervisor that you've probably seen before. There is no user space. There's a custom memory manager. And the most important aspect of the hypervisor is that it only executes when the instance asks it to. The word we use to describe this is quiescence. We try to make sure that the Nitro hypervisor is quiescent and that it doesn't interrupt guests unless the guest is actually asking it to emulate one of the instructions that traps or something of that nature. The whole goal is to keep the hypervisor as simple as possible. And one of the great things about keeping the hypervisor very simple is it's given us a lot of flexibility in our ability to support different types of hardware. Last year at reInvent, we introduced the A1 instance type. And the A1 instance type is based on an ARM processor instead of an x86 processor. Throughout this talk, I've been saying x86, x86, but it turns out that we really don't care about what that processor is anymore, at least from a virtualization infrastructure perspective. And so that makes it much easier for us to explore different types of architectures. And in the last year, we've introduced our own ARM-based SoC with the A1 processor. And we've also introduced AMD processors into our fleet again. So the more and more we develop this Nitro system, the more and more we're far less focused on what the customer processor is, and we're more interested in what the rest of that system is, because ultimately that is really what defines the system. I wanted to show a bit of an example of what we've achieved with the Nitro hypervisor in terms of jitter reduction. So this is always something that's a little hard to explain to customers, but inevitably when you're having jitter problems, you notice it and you're very unhappy about it. So whenever you're running a workload in a hypervisor, you always run the risk that the hypervisor is going to interrupt your workload to do something else. Sometimes this doesn't matter if your workload is not contended. Sometimes this can mean that you have one instance that's running slower than another because the hypervisor is interrupting you more over here. And again, variability is the enemy of distributed systems, right? That's a really bad place to be. So there was one customer that I was working with maybe about a year ago, and they wanted to bring a real-time application into EC2. True real-time applications that have hard deadlines on response times are extremely hard to get right in a hypervisor. There are very few hypervisors that can actually offer real-time guarantees. And to have true safety-critical real-time guarantees, you really have to do formal verification. There's no other way around it. So I don't pretend that the Nitro hypervisor is a real-time hypervisor. And so when they came to me and they said, hey, we have this workload, it needs to respond in 150 microseconds upon receiving a packet, my first reaction was, well, you have to use bare metal, because you have to run a real-time operating system on bare metal. It's the only way to get it done. Fortunately, we're able to offer bare metal with Nitro. And so the bottom red line is the i3 metal jitter performance. So what this graph is for a 48-hour period of time, we were setting a timer that would wake up in 150 microseconds, and then we measured the gap in that wake-up time, and we did that on every single core in the system. So with i3 metal, you see exactly what you would expect to see in a real-time operating system. Very consistent performance with a slight uptick at the high percentiles. It's almost certainly something like SMM, some kind of BIOS or firmware system jumping in, taking a few cycles, but it's not that bad at the edge. The yellow line is the C4 instance type, and this was one of our last Zen-based instance types. I would say that this line looks like what you would expect a traditional hypervisor to look like. Now, I think we put a lot of effort into optimizing C4. I think that line is going to look better than pretty much every other hypervisor out there. But you can see at the P70 or so percentile, we start breaking the SLA. And then at the P100, it's just way off, right? You're in the milliseconds range. And that makes sense. A scheduler jumps in, you get stuck in a spin lock in the kernel. You're just going to run into these cases, especially over a 48-hour period of time. What was a bit of a surprise to me is that C5, the blue line, looks very much like the bare metal line. Now, I'll remind you that with C4, we were actually reserving 10% of our cores for just the hypervisor. That was just like extra space for the hypervisor to do its thing. So we were only offering 90% of the cores to the customer. With C5, we offer the customer 100% of cores. So we're not giving ourselves any slack in the system. And still, even while doing that, you see that the line is almost at the same slope as the metal with a slight offset, and that's just because of interrupt delivery overhead in a virtualized environment. But the key thing is that at the P100, the uptick is basically the same as bare metal, and we never violated the SLA for this benchmark. So my big takeaway from this is that this type of I/O offload to dedicated hardware allowed us to make a massive simplification in the actual hypervisor and really did get us to a point where we have characteristics that are much more like bare metal than a traditional hypervisor does. So what comes next? So we've put all of this effort into building this hardware and software platform to provide a dedicated virtualization experience. But not all customers today are able to bring their workloads into a public cloud. Sometimes this is because of latency. Sometimes this is because of the amount of data that needs to be processed at a particular place. And so at last year's reInvent, last November, we announced a new project called Outposts. And this is a project where we'll actually be taking the same Nitro hardware that we're using in our data centers, and offering it for customers to run wherever they'd like to run it, in their data centers, in their back offices, anywhere that it needs to be. And it uses all of the same underlying Nitro hardware and software, and you can access it using all of the same interfaces that you would with any other cloud instance type. So this is really kind of where we're going with this system. Is we want to make it not just available in the public cloud, but also make it available anywhere that customers may need it. So that was it. That's the last slide. I'm happy to take questions if anybody has them. Thank you. There's microphones here. If you could go to the microphone to ask the question. Or if that's practical. Do we want to go ahead, just ask, I'll repeat it. Sure. Yeah. Sure. So the question was about a sort of a partnership opportunity. I would say to just come up to me afterwards and we can talk about it. I'm happy to have a conversation about it afterwards. Yeah.
So right now you say Santa Cruz. You have not talked anything about security in the sense of side channel. Are you doing anything special there, partitioning or configuration, or not?
Sure. Yeah, side channel security could be a whole other talk in and of itself. So let's see, where to begin with that? So there's a few things that are fundamental to how we think about virtualization. The first is that we never allow two instances to occupy the same core simultaneously. So very specifically, a lot of the side channel concerns that have occurred in the last 2 years or so have been L1 cache sharing, right? And the ability to observe L1 cache from another thread. We have never actually shared L1 cache across instances simultaneously. So we were actually less impacted by some of these side channel concerns with Spectre and Meltdown than a lot of other folks. The other thing that I didn't mention in the talk, but is a really important part of the Nitro system, is that all of the components in the system have a capability we call live update. So we can update any of the code in the system, whether it's on a Nitro card or on the hypervisor itself, without any downtime or perceivable downtime to customers. And again, this is only possible because we rebuilt literally all of the software from scratch, and we added this capability. So a lot of the practical impact of side channels has been that various vendors have been introducing new mechanisms or providing recommended mechanisms to do state clearing between tenants. And because we can actually update our software across the fleet without impact, we're able to move very fast in terms of doing these state clearings. But
for example, you can have row hammer issues across core instance. You don't do a quality of service guarantee separation.
Sure.
You can have those issues. Do you have any quality of service guarantees?
Yeah, there's a lot of mitigations in place for things like row hammer. So generally speaking, with row hammer, and this is all like very general, but I'm happy to get into very specifics, but row hammer has mostly been demonstrated on non-ECC memory. A lot of DDR4 has specific row hammer mitigations. So we spend a lot of time making sure that we're on top of the latest research with respect to things like row hammer. And I'm happy to talk more about specifics offline. Let's go this side.
My name is Rohit Gupta from Western Digital. I have two questions. One is about how do you see a future of the on-prem infrastructure as opposed to public cloud? And second is, in many of AWS services, I noticed that you can buy 2 vCPUs or VMs per CPU. Is there a reason for restriction for only 2? Why can't I go beyond that? Thank you.
Okay, so for the first question, the future of on-prem, what we want to do, we think that operating in a cloud-like model where you don't have to worry about wear leveling, for instance, that somebody else takes care of that for you, we think that's the future. We think that is where everybody wants to be. We think that most people are going to be better served being in the public cloud. There's really no reason to host your own data centers. Hosting a data center is a huge amount of work to do well. But for the customers that really do need to have something local, that's what Outpost is for, and that's how we think we can satisfy that need. The second question, I'm not sure I entirely got it, but I think it was about why is there 2 vCPUs per physical CPU? This is just the topology of hyperthreads today on popular architectures. There's nothing that would prevent us from having more hyperthreads per core. It's just that that's what most CPUs support today.
My name is Ming from Cerebral Systems. My question is, do you guys do anything other than dedicated GPU for GPU virtualization?
Okay. As of today, we only do dedicated GPUs. So GPU virtualization is a fundamentally hard problem, right? GPU interconnects are very fast. I would say that there hasn't really been a hardware platform today that has been designed to be multi-tenant. So with all of the Nitro cards and all of that I/O acceleration, we built that from day one to be multi-tenant, and it's very hard to take a piece of hardware that wasn't designed to be multi-tenant and make it into something that is multi-tenant. But this is something we're always looking out for, and at last year's reInvent, we announced something called Inferentia, which is an inference chip. And as you can imagine, this is something that we've been thinking about since day one with Inferentia. So we are working in this space, but so far, I think the other GPU vendors haven't quite gotten there yet. Over here.
Jim Ting from Samsung. Does a Nitro architecture have to evolve to support containers or microservices?
Yeah, sure. So I didn't talk about it in this presentation, but we actually introduced something last year's reInvent called Firecracker, which is a VM-based model for containers. And so we very much are looking at how do we adapt the Nitro system to support things like containers and microservices. And I guess the fundamental answer to that question is that because of a lot of the things like side channel concerns, we think that virtualization is really critical to achieve real multi-tenancy. And that's what we've been investing in. And that's actually an open source project. If you're interested in it, you can go and check it out. Next question.
Hi, Charlie Park from Intel. Thanks for nice talk. And then I have a couple of questions. So recently, Amazon AWS rolled out EFA, which is the evolution of ENA. And then can you talk about it a little bit? Second thing is, you talk about Jira management. And then is it only done by the controller, or do you do anything special to take care of the fabric?
Sorry, could you repeat that?
Take care of the fabric, like congestion management, all those.
I see, okay. So the first question was about EFA, and yes, I should have had a slide. I was worried I had too many slides. So one of the things we also announced last year, and we GA'd just a couple months ago, is something called Elastic Fabric Adapter. And this is a technology that's also built on top of the Nitro card for VPC that provides an RDMA-capable device to an instance. So for applications that are doing OpenMPI or any kind of high-performance message passing, it allows you to achieve the absolute lowest latency. So the half round-trip time for EFA between 2 instances is about 15 microseconds. And again, that's one of those things that the only way you're going to get to 15 microseconds is if you're passing hardware directly through to an instance. And with EFA, we're able to do that while also presenting a nice interface that we can support for a very long time, such that customers don't have to keep rewriting their applications depending on how things change. The next question was about how do we do quality of service, right?
Fabric management.
Congestion management. It's a complicated answer. So there's really two parts to it. So one is that we always want to make sure that that congestion just isn't a problem for customers that really need high performance. So if you have a 100 gig instance type, for instance, and you're doing EFA, our network is very, very big. There's a lot of bandwidth available. We make sure that we're not oversubscribing within a placement group. And so congestion just really isn't usually a problem at the high end. For smaller instances, where we're running a lot of instances on a single machine, we also don't want congestion to be a problem, but that's where we take more of a statistical approach. And we have a very large number of limiters that deal with everything from not just how many packets are you sending and how much bandwidth are you sending, but it also looks at what the relative cost of packets are compared to each other. If you have a very complicated security group, for instance, then the cost of processing a single packet is far much more than if you've got basically no security groups installed. So we've evolved our limiters over time to try to give a very even experience with customers, but it's also something we're constantly innovating on. So it's not a solved problem, I would say, but it's something that we're always working on.
Thank you.
Yeah. Over here.
Yeah, this is Vigyan Singhal from OSCE. I think you suggested that you could verify the real-time guarantees with hypervisor using formal verification. Do you have any details or reference for that?
So I specifically said that it's hard to be a hard real-time system if you haven't done like formal verification. We haven't done that with the Nitro hypervisor, although it's something that we do a lot of formal verification, but we've not verified like real-time characteristics. The one hypervisor I know of that has actually verified real-time characteristics is SEL4. So they actually have proofs of longest path within the hypervisor. And so they can actually make very strong statements about this is the maximum amount of jitter based on the physical hardware model that they use that you can possibly see. So it's definitely possible. It's not something we've done yet, but it's certainly something we're interested in.
Okay, maybe I'll follow up offline.
Yeah.
For the Nitro outpost, do you have a plan for just not x86 solutions, but other ARM solutions and AMD solutions in the future, or
Yes.
is it currently available?
So we intend on supporting all of the platforms we support in the public cloud today. And so we have AMD offerings. We have ARM-based offerings. It's our own ARM chip, Graviton. Right. And we intend on supporting those things in outposts also.
Okay, then just an additional question following that. Do you believe that the Nitro system, a solution like a Nitro system, can make the popularity of the other systems in the data centers in the future?
Sorry, could you repeat that?
Can you, do you believe that the Nitro systems can allow other systems, other processors more popular?
I see, yes. Yes, the answer is yes. So I think that because we have so few requirements on the actual x86 core, or really any core, it's not that hard for us to introduce and support basically anything that speaks PCI. So I'm not saying we have any specific plans here, but if there was a compelling processor, as long as it supported PCI, I think we wouldn't have that hard of a time supporting it. And if there was customer demand for it, we would certainly look into it.
Andrew Putt at Microsoft. So the Nitro card's a 100G card, but I was looking through the instances that are available, and only a handful of them actually support 100 gig networking. Do you know whether it's not more available if it's been in everything since 2017?
No, the 100 gig is the 4th generation card. And so that was only launched at the end of last year. And so it's the new things that are starting to support 100 gig. Previous to that, it was 25 gig, and then previous to that, it was 10 gig. So as we've been iterating on the cards, we've been jumping kind of fabric interconnect performance over time. Okay. But it's safe to say that all of the future instance types will likely be 100 gig capable. So.
Right, maybe I can insert a last question. So since this is an audience mostly of hardware people, any last advice for hardware designers that are building things for that may end up in a cloud data center?
Absolutely.
You've already mentioned a few things around QoS, anything about features, functionality, cost, performance? That'd be great.
Yeah, so just as a general observation, so I've had the fortune in my time at Amazon to work very closely with hardware designers through Annapurna Labs. And I think the things that have been most successful for us is to work really closely in lockstep and to integrate or to iterate very quickly. So in the last, I guess, 5 years, we've gone through four generations of hardware technologies. That's a very fast iteration cycle. And being able to iterate in hardware like you would iterate in software ends up being super critical. The second thing that's really a detail of the way the Annapurna technology works is that it is very software-centric in terms of the way the hardware works. So just as like a detail, all of the physical devices on the SoC present the same interface to software. It's pretty typical that you won't do that kind of standardization like in an SoC, but it makes it easier for us to support new SoCs. And as we go generation to generation, we end up having to throw away a lot of code and write new code. This is because we're trying to take advantage of the underlying hardware. So finding that nice middle ground where you're not making software people go crazy and they can actually take advantage of the underlying bits, but also still iterating quickly, I think is super key to being successful. So.
Okay, let's thank Anthony for a great tutorial.
Thank you.
All right, let's move to the second tutorial. We're going to stick to Seattle-based cloud companies. So it's a great pleasure to have the second tutorial be given by Derek Chiou, Eric Chung, and Susan Carrie. Eric actually couldn't be here today, but he did a lot of work on the tutorial anyway. So Derek and Susan, they're both architects for Azure. Derek also has a long history with hot chips as well from his previous career as an academic. And they will tell us about how Microsoft approaches acceleration for the cloud from their own infrastructure all the way to machine learning applications.
All right. Okay, so we're going to be talking about acceleration at Microsoft, specifically focused on the cloud. So Microsoft's cloud is actually very, very large. It doesn't just consist of Azure. We have many, many properties through Microsoft. Pretty much anything that you remember or used in the past or currently from Microsoft is available in the cloud. So for instance, Bing was started in the cloud, but Office 365 Exchange, SQL Server, Xbox, OneDrive, all of these properties within Microsoft are running in our cloud. So there's a really, really broad collection of workloads that we can draw on and look to accelerate. So in order to be efficient across all of these different properties, what we want to do is we want to share as much as possible between all the engineering and infrastructure. And we want to try to get business efficiency from all of these different potential opportunities. So motherboards, firmware, BIOS, server configurations, actual machines, whether we can share machines between properties, the networking and storage infrastructure, and so on, are all things that we want to try to share in order to increase our efficiency. So how did we, do we, and will we efficiently accelerate Microsoft's cloud? We'll share some acceleration examples of what we've done. We'll share some of the philosophies and some of the approaches that we've taken to acceleration. And we'll focus on two of the examples towards in the second half of this talk. So one thing that I need to point out is Microsoft is accelerator agnostic, right? So for instance, in the AI world, we use CPUs, we use GPUs, we use FPGAs, we use MPUs, we use ASICs. All of these are, we don't take a position on what we do. We try to use whatever is the best tool for the job. And so we have instances of all these within our AI portfolio. So the benefits of cloud acceleration at Microsoft is really our ability to interact with our first-party internal development. This is something I've done acceleration in the past, and I try to convince people, hey, this is a great way to accelerate. And if I'm talking to another company, I've got to go and say, oh, well, first of all, I've got to go and sign NDAs, get an agreement to meet with people. We can't talk very openly and so on. The fact that we're doing this acceleration from within Microsoft is really, really beneficial. No legal issues. We can actually see the code directly that we are trying to accelerate, share detailed requirements, not just between a single acceleration project, but between acceleration projects that allow us to potentially go and leverage each other's work and allow us to become more efficient. Can share internal success stories. This is actually very, very valuable that we found within Microsoft. We can draw from internal development resources, and we can partner directly with developers and the users of this. Our users are mostly our first parties, are other people who work for Microsoft, rather than external customers. At least that's the way a lot of the acceleration work that Sue and I have been doing has been targeted up until now. So for example, many of you know that Bing went and accelerated ranking on FPGAs. This was, we published in 2014. We had a deployment, and this was something that Azure Networking saw as a potential way for them to accelerate some of the work that they needed to do. Bing's deployment was a success story. Deployment is very, very important for us in order to prove that something will really work. Once there was some, we could share the success story. We started architecting. We borrowed actually developers and architects from the Bing teams and move them and use them to help accelerate the networking. We leveraged a lot of the old code ideas and infrastructure in order to do that. Then what we did is we re-architected our board and our systems in order to be able to support both the Bing workloads and the Azure networking workloads. That would allow us to effectively share that engineering effort. Okay. Can I help? Just represent. Is that? Okay, all right. So some of the specific requirements for those of you who haven't accelerated in the cloud, there are actually some things that are kind of unique to the cloud that we didn't realize when we started, from people who are used to accelerating not in the cloud. One of the things that I mentioned before is deployment is king, and I can't emphasize that enough. When I started working in Bing, my first boss said, I don't believe any code's going to work until you deploy it on at least 1,000 machines, and really he'd prefer 10,000 machines. Because people find all sorts of interesting problems once you get to a reasonable scale, and a few hundred machines or tens of machines, a couple machines in lab are just not sufficient, right? So this is really when cloud providers, or at least Microsoft, will really start believing you. Many deployments have challenged. We've seen very interesting interactions between components. We've seen cases where hardware fails, and the hardware vendor comes back and says, this is a 1 in a million instance. Well, it turns out if you've deployed more than 1 million instances, you actually start seeing these problems. And we've seen some really, really crazy interactions between a bug in a BIOS that occurs at a very specific point with a BMC reboot that then causes power down to a specific component, and everything, you don't actually see the bug because all these things occur at the same time. So that deployment is really, really important for us to really believe in what we're in the acceleration capabilities. The other thing is a lot of times you'll see optimized servers. So when we're thinking about acceleration, on the outside, you might think, oh, I can just plug a card in here. There's going to be plenty of slots. There's going to be plenty of I/O bandwidth. That's not always true. It depends on the servers that have been deployed, because in the cloud we may go and optimize heavily in order to try to reduce costs. Power is an incredible concern for us within the cloud. If you go there are certain limits of power that's available to a chassis, a row, and a cluster. And these particular power limitations will fundamentally limit what you can do. So if you are going to use 10 or 20 additional watts for an accelerator across all of your servers, that may actually result in one less server in that rack, which is one less server worth of capability that you can offer to your customers. The other thing is fans take a lot more power than people think. This is something that we've all learned quite a bit. The scale is really, it's kind of interesting cloud scale. Cloud is one giant machine with millions of nodes and customers, so it's very large scale. But on the other hand, if you're talking about building an ASIC and the NREs involved with an ASIC, it's really not that big. We're talking about order millions per year. So this is something where if you're going to be paying a reasonable size NRE for hardware for an ASIC, that's something that you really need to consider as to what size really makes sense and what kind of benefits you're going to have to make sense. Sharing between applications can increase volumes and reduce per unit cost. So if you can find some synergy between your applications, that could be a real benefit to you. Reliability, availability is sometimes extremely important when you're talking about Azure, where we don't want our customers to reboot. You know, we basically, every bit of reliability that we squeeze out of the hardware and all of the infrastructure around it to make that hardware even more reliable, that's critically important. If I'm doing a Bing workload that's, has to, is dealing with a machine learning model, an individual bit flip may not be as important as in the Azure cloud. Well, we really need the ability, no matter what, we need the ability to diagnose and repair without physical access. This is actually something that's also very important for in the acceleration world, where a lot of times we expect that we can plug a JTAG cable into our board in order to debug it. Multi-tenant support is obvious for a variety of reasons, and security is extremely important within the cloud. This is something that you have to harden against internal, external, and physical attacks. Obviously, there's going to be costs involved, and how much you do really depends on what you're doing. But fundamentally, this is something that's critically important, and isolation between customers is also critically important. All right, so if we take a look at acceleration, the traditional acceleration categories are FPGA, ASICs, and GPUs, right? That's what people say. I'm accelerating with an FPGA, I'm accelerating with an ASIC, and so on. Microsoft uses all, but not obviously in the same numbers and the same fractions. So these can be done either as a discrete package. I can have a discrete FPGA, a discrete GPU, a discrete ASIC, or I can incorporate this IP on chip into an SoC, right? This is kind of the two possible options. All things being equal, specialization is the root of efficiency, right? If I'm talking about the same technology node, talking about the same basic problem, if I can further specialize, I can fundamentally increase my efficiency. So what I want to do is I want to eliminate all of the overheads unnecessary for the functionality I need to support. So for example, if 4-bit numbers are sufficient for DNN inference, why do I need 32-bit data types, right? Fundamentally, that's something which I'm losing efficiency by having an ALU that's more than I need. Accelerators are obviously more efficient because they are specialized compared to cores. However, specialization increases costs, right? So there's engineering costs. Now I've got to go and build another piece of silicon, or I've got to go and develop for another piece of silicon rather than just running it on the standard CPUs that I've had. I need to integrate, into the application or into the system. I need that, now all of a sudden there's an additional team that's doing work that's, potentially going to affect my agility and time to market, right? So we need to consider all these. There's also business costs. If I have two different kinds of ways of doing things, I need two different classes of spares, right? If I'm using an FPGA in addition to my CPUs, now I've got to go and spare FPGAs in addition to CPUs. Reduce volumes. If part of my fleet is running GPUs and part of it is running ASICs, that kind of bifurcates my fleet, and it makes it, there's additional management issues, but also it reduces the volumes for each component, which obviously potentially impacts price. So there's a fundamental trade-off between the specialization to get efficiency and the costs involved of doing that specialization. So our traditional acceleration categorization is really product-based rather than architectural structure or capability-based. And so what I mean by that, what's an FPGA? So most people, when they think about FPGAs, or a lot of people when they think about FPGAs, they think about lookup tables, they think about routing resources that connect them together. But if you look at really what an FPGA is today, this is a picture of a Stratix 10. Xilinx, this is an Intel Stratix 10. Xilinx has very similar kinds of architecture, but there's an internal reconfigurable fabric, which are those lookup tables and routing resources. But on the outside, there are these hardened transceivers. These are standard, PCI controllers, Macs. They're hardened. They're basically as you would buy in any ASIC. DRAM controllers hardened as well. And even inside the FPGA, there's a bunch of hardened components. For example, there are 32-bit floating point DSPs in FPGAs these days. There's very, very efficient dual-ported SRAMs, and so on. And so what winds up happening is these devices become not just the original lookup table, but it's actually it becomes a mix of kind of hard fixed functionality and the reconfigurable logic. Likewise, ASIC is often talked of, it's very nebulous, right? The acronym Application-Specific Integrated Circuit really indicates that I've got a single fixed function or a small number of fixed functions that ASIC can produce. but a lot of people call ASICs and network processors ASICs as well. So fundamentally, the ASIC kind of term is not very precise anymore. When I was a grad student, we actually used an ASIC, which was a 32-bit floating point unit. We aggregated 2 of them together to get 64 bits. That was an application-specific integrated circuit. These days, ASICs really kind of fit more inside of a chip rather than as inside of a SoC rather than as a chip itself. And GPUs are kind of the NVIDIA, AMD, and so on. And GPUs have changed dramatically over time as well. If you think about what GPUs were 20 years ago, they were really intended for graphics. Now they're really kind of a data parallel SIMD-like execution unit. All right, so here's an alternative hardware accelerator categorization that we're using more within Microsoft. We have this concept of fixed function, mostly single function. So you can think of this as a PCIe controller, Ethernet controller, a DRAM controller. These are things that really not fundamentally going to change, right? And they may have some configurability. My PCIe controller may have a Gen 3 capability, Gen 4 capability, and so on, but it's not going to, we can't change that PCIe controller into a Ethernet MAC, right? So fundamentally, it's fixed function. And generally, those kinds of fixed functions are best implemented in fixed logic, which this is a specialized hard circuit. This is what really was the original meaning of ASIC, right? Then if we look at the rest of the world, the rest of the silicon really needs to be programmable in some way. Right, what that means is that, and we really see there's 2 ways to program. There's the circuit level programmability, basically like FPGAs, which do lookup tables and routing. And there's micro-instruction programmable, which basically I have some sort of control, which is my instruction. I have to fetch these instructions or micro-instructions, and then I go and execute them in order to implement the functionality I need. Right, this is really needed. We really need this programmability when functionality changes over time, and enables optimization over time as well. It allows me to, I can tune my circuit in an FPGA, I can tune my code in a processor, right? One thing that has been, happens a lot is circuit programmable FPGA-like logic is often compared to fixed logic. People take the same RTL, and they say, I'm going to compile it to FPGA and ASIC, and everyone knows the FPGA is going to lose there. Because fundamentally, what's going on is that you're paying an interpretive tax on the FPGA to interpret that circuit. Right, you're using a lookup table instead of a hardwired logical gate in order to implement things. So it's very clear that the fixed logic is going to be more efficient. The FPGAs generally are an order of magnitude larger, slower, and less energy. That's the conventional wisdom. Turns out it varies on each one of those metrics, but that's the fundamental conventional wisdom. So better comparison really is between programmable components, a circuit programmable like an FPGA, or an instruction programmable like a specialized processor. So programmable trade-offs, the circuit programmable device, is clearly, it's got inefficient gates, but what it does have is a very efficient circuit. So I've got those lookup table overheads, but I have a very efficient, potentially the ability to build a very efficient circuit. Likewise, instruction programmable, I have very efficient gates, but then I may have the processing overheads that come with building a processor. So one example that we can potentially use is crypto. So if I've got to implement crypto on my part, right, whether it's however I'm going to do it, I'm going to implement this. So what I can do is I can go and implement a dedicated circuit, right? So if I'm implementing in a circuit programmable way, I can go and implement the exact algorithm I need, AES GCM 128. I don't need to support CBC. I don't need to support XTS. I don't need to support 192, 256, 512. I implement the exact circuit I need. And by doing that in a circuit programmable way, it makes it much more efficient. That circuit is going to be much more efficient as a circuit than something that's implemented in a programmable way, which I might have to support a bunch of different standards, which either what I'm going to do is I'm going to go instantiate each one of those standards as an individual circuit, or I'm going to build some sort of micro-coded machine or micro-program machine in order to be able to implement all those different standards. Right, so fundamentally, these are kind of the 2 approaches. One allows me to go, if I go and implement it in a micro-coded way, I can go and change that crypto algorithm on a packet-by-packet basis or block-by-block basis. If I go and implement a circuit, a very highly specialized circuit, I can't do that. I'm stuck with whatever I have. In a circuit programmable way, I can go and change that over time, but fundamentally I'm stuck with that. But when we look at the efficiencies of having that highly specialized circuit really does wind up overcoming a lot of the interpretive overhead you might find in a programmable, instruction programmable circuit. All right, so Microsoft's hybrid approach is really to try to use the best tool for the job. And this really is balancing those efficiency gains with the cost of specialization at the solution level. accounting for business concerns and leveraging others' works and hardware. So best depends on many, many factors, such as solution performance, power, cost per unit, and time to market. That's kind of looking at the accelerator itself. And then looking at how that fits in to the overall solution in terms of the stability of the algorithms, the size of the opportunity, the NRE involved, and then the opportunity cost, the delta engineering cost, iteration speed, and when does the engineering need to be done. One of the things here is the opportunity costs are very severe. Hardware designers are very hard to come by these days, as you probably all know. It's very hard to hire very strong hardware designers, and so what winds up happening is we have a choice of doing two different projects. Which one is the better project from the overall opportunity cost for the company? You really want to be able to reuse deployed infrastructure if at all possible. It's that reuse that we like to see that allows us to become more efficient and allows us to deploy much more quickly. It's going to be business issues, volumes, partnerships, legal, export. There are certain technologies that you can export. Other technologies are harder to export. And there's a competitive position. We may have to react to a competitor. We may have to take something that takes a shorter amount of time in order to get to that reaction, in order to react in a timely fashion. All right, so we're going to talk about two examples. The first example, which we're not going to talk about, is really a circuit programmable example. Accelerated networking is basically our ability, our offload of software-defined networking. We do this on FPGA. We do this in a very, very circuit programmable style. Our circuits are highly optimized for the particular work we want to do. Provides low latency, flexibility to adapt to rapidly changing network needs. We've got a paper that was published in NSDI 2018. We'll refer you to that. I'm going to talk a little bit more about the circuit instruction programmable approach we've taken for our machine learning workloads. Eric Chung was supposed to be here to give this portion of the talk. I'm going to do it for him. But that's going to be, we're talking about the DNN inference on Brainwave. And we also have a lot of publications on that. There's one of them that I've stolen a lot of figures from. And then we're going to talk about fixed function acceleration. Sue will be talking about that, this Corsica compression, encryption, data integrity. All right, so let's move to Project Brainwave. So Project Brainwave is a scalable DNN serving platform. The intention is for it to be very fast, latency, and high throughput serving DNN models without requiring batching. So within Bing, batch size of 1 is very, very useful in a lot of cases, and so we went and tuned Brainwave specifically to target batch size of 1. Flexible, the deployment of FPGA can be adapted to fast-moving AI algorithms. One of the things, those of you working in AI, it seems like there's a new algorithm literally every week. And we need to be able to adapt to those very quickly, and we want to do that in a way that's very efficient, timely, and cost-effective. We also want this to be friendly. Turnkey deployment of pre-trained models in popular frameworks. We want to support TensorFlow, PyTorch, and so on. We want users to be able to go use those and be able to access models that have been pre-trained. So the pre-trained, basically the flow is we have some sort of pre-trained model. We're only talking about inference here, not training. We have some sort of pre-trained model. It gets distributed across a wide number of FPGAs that are living across our data center. And then on each one of those FPGAs, we're running a Brainwave soft MPU, which goes and executes that particular model and produces results. All right, so it's been in production since 2017. This is within Bing. We deployed a deployment of LSTM-based NLP models. There's tens of millions of parameters, and it takes tens of milliseconds to serve on a well-tuned CPU implementation. Where for us, we're significantly faster than that, roughly we're roughly an order of magnitude faster, right? And we also have very, very good tail latencies in this as well. Tail latencies are critically important for Bing. We want our searches to happen quickly. We don't want some search to take a lot longer than it should. So tail latencies in Brainwave-powered DNN models are negligible in end-to-end software pipelines. So this is including all the software. Fundamentally, we are seeing very, very low tail latencies. So the Brainwave soft MPU, there are three main objectives in the design. The number one is optimizing for no batch inferencing. So fundamentally, that batch size of 1 is critically important. Number two is simplify programmability and targetability with a single threaded control. I'm not going to talk much about this, but unlike a lot of the other AI chips, we're a single threaded control. It looks like a sequential piece of C code when we're programming this. We want to balance instruction granularity and flexibility, so we abstracted basically to matrix vector and vector-vector operations of some native dimension, and that native dimension actually changes based on the hardware that we're running on, the FPGAs we're running on, as well as the applications that we're looking at. And they're composable and diverse models, RNNs, CNNs, and so on. And the other thing that we're doing is we're doing instruction chaining, which means that the output of one operation can be automatically fed to the next operation. So what this does is we don't have to go and write things back into memory or write things back into some register. We can just have data kind of flowing through and being very efficient. The FPGA allows us to do this by allowing us to go and implement different functional units when we need them and replacing them, replacing some function with another function and then kind of crafting the path back into something that's easy to have instructions pass the output of one to the other. So dominant compute patterns in machine learning, deep learning is really matrix multiply. And so there's basically three different approaches that we can take when we do vector-vector, matrix-vector, and matrix-matrix. What we're doing within Brainwave is really focused on matrix-vector. This allows us to get the kind of performance we want and also allows us to get to the batch size of one. So isn't matrix-vector memory bound? Isn't that the standard problem? Well, what we do is, rather than trying to run on a single part or a small number of parts, we actually can distribute our model across a large number of FPGAs. And the more FPGAs we have, obviously, the more internal SRAM bandwidth we have. So what we do is we go and map our weights into the SRAM that's present on the FPGA, rather than trying to map them in DRAM and cycle through. And this gives us obviously much higher bandwidth. We use more FPGAs, in this fabric of FPGAs that we have throughout Microsoft. We use the number of FPGAs we have to spread across, and then we get obviously the efficiency improvements on the single FPGA itself, and we use the multiple FPGAs to implement the larger models, right? So the intention is to kind of get to solve two problems with one basic architecture. The microarchitecture of one of our MPUs looks something like this, and obviously it changes based on the exact models that we're running. But fundamentally, we've got a matrix vector multiplier up at the top. It's got a bunch of memory. It's got memory that's associated with it. And then what will happen is we'll go and execute the various instructions, and we'll pass through these various crossbars where they've got multiple functional units attached as well. And these multiple functional units can change based on the model that we're running. So for example, here, I'm going to read my vector x, I'm going to multiply, I'm going to add, I'm going to do basically a series of instructions. This is that sequential instruction stream that I was talking about before. And then what happens is these all wind up being very, very large, and very, very large vectors and very, very large matrices, but distributed across many different FPGAs. And so basically your data flow kind of starts at the top, you go and do your initial matrix vector multiplication, then you pass through the various functional units you need. You can go back and forth, and then you wind up rewriting your result back at the end. Notice that we are not trying to write back the result after each cycle. We're just passing through, basically through registers, pipeline registers, to go to the next stage. So what we want to try to do with all of this is we want to scale this matrix vector and the functional units. So in order to scale memory bandwidth, we do this by tiling the engine. So it turns out that we're just showing one. Obviously, there's a huge number of these that are implemented on each FPGA, and then we go across multiple FPGAs as well. We also go and optimize on data types, and we also optimize on scheduling. Talk a little bit more about the data types here. So one of the things that we've discovered, and many other people have as well, is you don't need 32-bit floating point. You don't even need 16-bit floating point to do a good job with inference. In fact, in our studies, we found that 8 to 11 bits is generally sufficient. There are cases where fewer bits make sense, but what we've done is we went and optimized around this Microsoft 8-bit. So in cases 1-bit sine, 5-bit exponent, and 2 to 5-bit worth of mantissa. So what we did is, rather than going and trying to use the DSPs that are on the FPGA itself, which have these 32-bit floating point capability, we went and implemented these MACs, these multiply accumulate structures inside of the soft logic, optimizing for the data type that we felt was reasonable for us. In this case, we've got 96,000 of these Microsoft floating point 8-bit MACs versus the 5,700 that are on the FPGA itself. This gives us 16 times more efficiency, both in terms of area and in terms of energy and obviously performance, right? So this gives us, by using these different data types and by being able to iterate on the various different data types over time, we were able to come up with this, and this allows us to go much, much faster than if we were using the native hard structures on the FPGA. So if we look at the performance numbers, these are actually all in the paper, so I know this is an eye chart, but fundamentally, what we want to call out is that the percentage utilization, when we're talking about batch size of 1, in this particular application, we're seeing about 36 teraflops, and we're getting about 75% efficiency. When we're comparing it to Titan XP, we were seeing this was only 3.3% efficiency and 0.4 teraflops. So fundamentally, we know that there are newer FPGAs that when this paper was published, this was the best, we know there are newer GPUs, this was the best GPU we had when the paper was published last year. Likewise, I'd like to point out that Bing Intelligent Search is backed by Project Brainwave. Fundamentally, Bing Search is run every time on these FPGAs running Brainwave. So anytime you search in Bing, you're using FPGAs. This, again, is an eye chart, but fundamentally, the point here is that we're seeing an order of magnitude better throughput, and we're seeing an order of magnitude less latency with much better jitter than we see in software. So fundamentally, this is something that we find to be very, very useful. So Project Brainwave has really been optimized for the Microsoft Cloud. It's inference optimized, it's software programmable NPU deployed on a circuit programmable FPGA. So that's one thing that's important. We're using instruction level programmability. We're using it as what FPGA people like to call an overlay. It's basically we're implementing a soft NPU on top of the circuit programmable FPGA. So initially target for Bing with a batch size of 1, but we've actually exposed this capability in Azure ML, so you can come and use these capabilities if you like as well. The rapid iteration enabled by the FPGA allowed us to do very, very quick innovation. So we actually went through many generations, many explorations of figuring out what the best structure was for the NPU as well as the best data types. And this is something that continues to go on today. Other than the data type specializations, though, the architecture is completely FPGA agnostic, right? So although we're doing all this work on FPGAs today, this doesn't mean that at some point in the future, this could be ported to other technologies. The network attacked FPGAs really affected the design. So when we did all of this, we started with Bing, obviously. Those of you who've seen the original papers, fundamentally, we were looking at attaching the FPGAs together in a 2D torus of 48 total FPGAs. After Bing Networking wanted to get involved, they wanted a bump-in-the-wire architecture. So fundamentally, we allowed each one of the FPGAs to be attached to our data center-wide network. So all of a sudden, we got a lot more FPGAs. So that's something that allows us to go and think about using more FPGAs to implement bigger models and thereby be able to use that pinning all the weights directly in the SRAM. That's one of the reasons. Obviously, we looked at pinning in the SRAM before the networking as well, but that allowed us to actually scale up to reasonable size models. We leveraged the existing FPGA work, and they contributed back to the FPGA effort. So all the Brainwave work was founded on the basis of the boards, the shell, which is the basic hardware abstraction layer, the drivers, all of that work that was being developed for the FPGAs, for the original Bing FPGA work, was all leveraged by the DNN work. And the DNN work, the Brainwave work, has all been contributing back to the overall engineering effort across Microsoft and FPGAs. So we use the deployed FPGAs that are already there for Bing. We use the infrastructure, we use the tooling. Engineering for reliability, availability, lifecycle support, and scale. I didn't talk about this at all, but this is a heavy, heavy emphasis within our Bing deployments to be able to go and maintain and service the deployed fleet. We're currently deployed at scale in first-party services such as Bing. So as I said, Bing Search is being powered by this technology, and it's available to third-party customers through Azure ML, which I mentioned. Okay, so I'm going to hand the talk over to Sue Carrie.
Good morning. I'm going to be talking about Corsica, which is an ASIC that we've done for the cloud, and I'm going to talk about why we chose to do this ASIC and also how the cloud affected the design of the ASIC. So we went and talked to a bunch of different first-party users, and everybody who stores data would like to compress it and encrypt it. And so this meant that there was a broad application for compression and encryption. Obviously, you want to do the reverse as well, and then everybody also wants to authenticate their data. One thing that was really key for us, which was reflected earlier in the slides, is our ability to have an internal party, namely storage, that was deeply involved in our architectural definition was really critical to our success. And this is the kind of partnership that's extremely difficult to get if you're not in the same company with the party that is doing the application itself. The things that were key for us based on the cloud is, well, we got from our partner, we got the encryption and which particular key KDF, which particular key usage, what was the entire sequence of processing that they need to do to integrate tightly with their application. What do we need to do at a system level, which really meant don't introduce any bottlenecks. Do not be the bottleneck in getting data stored, and that leads to a very aggressive latency requirement. And we also wanted to have high throughput to support multiple tenants, multiple uses, many cores. So this is a high-level diagram of what we've built. And you can see here, the actual work is in these purple boxes. This is actually doing the function that the user cares about. And this, by the way, we'll talk about this a little bit later, this is also what we open sourced through Open Compute Platform as Zipline. Now, in addition to actually doing the work, you want to do it for many users. So there's a bunch of stuff over here that has to do with the system integration. And so we've got SRIOV, we need to support security, schedule between things. And then this, while it's not a programmable element here, it's command-driven. There's the command processing. You can do a variety of things with this pipeline. One thing you'll notice is there's no memory here. Everybody says, where's the DRAM? There is no DRAM. Where's the big buffers? Big buffers in the memory. Nope, no big buffers. This is a streaming model. So if you said compress 8 megabytes, there's no 8 megabytes stored here anywhere. The storage inside of the chip is what is needed to look in the search window for compression, as we're doing an LZ77 type compression. And then it's streaming in and streaming out. In our model, we were envisioning CPU memory over on the other side of the PCIe, but it can be anything on the other side of the PCIe, as long as we can just access it through the PCIe. So if we look inside, actually what we're going to do now, we're going to look inside these purple boxes. And what you see is in the green, this is actually doing the work. We compress, we encrypt, and we authenticate. But we have a really high reliability requirement because we're in the cloud. We cannot lose customer data. You cannot have an alpha particle hit this thing while you're doing this data, and then when they go to decrypt their data, it's garbage because one of the bits flipped. So the first thing we're doing is, in addition to doing the work, we actually check the work. So we say, okay, did we get the data from the host correctly? The user can actually say, I'm going to hand you a CRC. Let's make sure it got there. We will compute a CRC so we can tell them it didn't get there. We go ahead, we do all of this work, then we reverse it. So there's no option here. If you're going to compress, encrypt, and authenticate, then you're going to reverse that operation, compute the CRC again, and then say, well, do these things match? So now our failure rate is determined by that matching CRC. And if we have failure anywhere in this entire pipeline, then we catch it. And that was driven by the storage requirements. It's what's done today. And if you don't do all of these steps, it incurs multiple passes over the PCIe and multiple trips to the software stack, both of which are bad. In addition, we do something else. Obviously, if we're going to be doing encryption, we're going to have a key vault, and we're going to generate keys. But it's possible to have, say, the alpha particle hit your KDF, and so you now have the wrong key. And in fact, if we have the wrong key and we only did this once, we could encrypt it, we could decrypt it, we could get the original data back. It's just that nobody knows what that key was that we used. So that's not really going to go over very well. So we actually did redundancy here and put in an entirely separate key generation for the decompression, for the latter part of this pipeline, so that when we check the work, we aren't subject to a single bit failure here. And that, once again, went towards the need for really high reliability. So if we look back at our original requirements, well, we want to share in a multi-tenant environment. So we have SRIOV, so you can access the device directly without going through the hypervisor. Everybody needs to be scheduled, and we have a more complex QoS scheme that accounts for the fact that you may have many VMs running or different levels of, multiple cores, say, doing a background activity while other cores are doing foreground activity, while other cores are doing a different foreground activity. The reliability was that check the work and the redundancy. In addition, as Derek had mentioned, it's extremely important to realize you cannot go out into the cloud and put a logic analyzer on your hardware. You can't access it at all. It's off maybe in Dubai, maybe someplace else. And we need to be able to understand if there is any kind of a failure at all, that the failure occurred, how much, get all the information that we need to diagnose that failure, get it remotely back to the people who can do that work. And so in the, I'm going to go back a little bit here. In this block here, we've got an ARM processor that is doing that kind of management for failure, and it's also doing support for security. Which is that it is supporting, we've got Cerberus supported, and that is a secure intermediary between devices and the NVRAM. And I think it's a little bit similar to what Amazon had talked about, actually. And so we're supporting that for boot. For our rest of our boot sequence, we've kind of patterned things after the Xbox, which has been proven because a lot of people really like to break the Xbox. It's been proven to be quite secure. We can transfer information across the PCIe, so we can get those keys without exposing them on the PCIe. And for SRIOV, we aren't just using it so that you can get at the device quickly. We're using that to provide isolation between customers, because we absolutely must not have one customer be able to see in any way at all either the keys or the data or anything for another customer. So we could have all those requirements, and we could say, hey, let's go ahead and do them in an FPGA. What would that look like? And we actually did see what that looked like. So here we can see, well, we wanted to have low latency, so lower is better. Here's Corsica on 64K, and here is the FPGA. Now, there's always this question of, well, you know, which technology node did you use for the FPGA, and which technology node did you use for your ASIC in this study? And they were comparable. And so this was squeezing one thread in, and this is, in the ASIC, able to support 4 threads. And with a smaller buffer, you see, you know, that gap reduces, but actually the percentage can be even greater. Because we can fit in 4 engines, if you go over to the throughput, you see this picture here where there's really a lot more throughput when you're doing the ASIC. Now, we were able to do this because the compression algorithms, when we began this project, compression, encryption, these are stable algorithms. So you can really tailor that hardware, and you don't get blindsided because, oh, you did a machine learning algorithm, and now this year everybody's models are 5 times larger. That problem wasn't there. There has been some movement since then, but we're still, this is at a zlib level 9 compression ratio, which is also another aspect of this. If we didn't get enough compression, then it was not going to be worth doing this part because we'd spend more on the storage. And if you look at these 2 solutions here, there's a comparison between saying I want to get more compression ratio and I'm willing to give up the throughput, where in the FPGA you're contained to this compression ratio at that throughput, and for the ASIC, because we could design it special purpose, then we aren't making that sacrifice. Now, I'd mentioned before, we open sourced to Zipline, and there's an interesting trade-off if you're looking at the cloud, because we're a customer of silicon. We're also a maker of silicon, a designer of silicon. And so we have a choice with any application area that we're looking at. If you look at an application area where you say, there's like special sauce, there's something that we're going to be able to do, maybe it's in machine learning, maybe it's in another area, maybe it's something special for our first-party user that we don't want to share with other people, where we think this will give us a competitive advantage, then you can do what companies normally do and keep it to yourself. If it's in an area that sort of everybody wants to do this, and you say, well, does Microsoft really want to be in the business of building this sort of building block that is commonly used across the industry even? Or do we want to be in the business of selling services like Exchange and SQL, et cetera? We'd rather be in the business of selling services. And so in the case of Corsica, it made sense for us to try to, or to help seed the ecosystem by releasing the heart of that pipeline, those purple boxes, to the community And we did that via OCP, and so we've released the RTL and the microarchitecture specs and an exercising test bench and the new compression standard that we had refined for our purposes, and we've released all of that, and anybody can use it, and it isn't like, well, what do I have to do to use this? You go to the GitHub and you use it, and that's about it. And there's where the GitHub is. So did you want to do the conclusion, Derek, or do you want me to? Okay. So when you're in the cloud, there are these requirements that haven't existed for the one-off systems on premises, whether it was a workstation or a mini cloud. When you're looking at accelerating in that environment, people have asked, we've had internal people say, well, what's your rule of thumb, FPGA or ASIC? And the answer is there is no rule of thumb. If you look at all of the considerations that come up, it's really hard to say, oh, here, and you can't reduce it to some equation. You really have to look at each case. And in all of these cases, you can also have the aspect of what's your strategic business approach come into that decision. We're doing multiple acceleration projects. And we are interested in enabling the ecosystem when it makes sense. And we've had a lot of people contact us about Zipline. If anybody here would like to contact us about Zipline or about something else where they think that that kind of a model would work, that would be great. And then we're hiring.
Right.
My name is Dan. I'm with Identify, a small startup that is actually doing data compression and indexing compression. Might be interesting. But anyway, the question is related to how a small startup like my startup or a small company can use your infrastructure. I saw some things. Can use your infrastructure to, say, develop prototypes that you can then use, to get the customers and kind of do the bootstrap. It looks like you are currently more appealing to bigger companies. So if you can elaborate on the process of how would I, as a small company, integrate into this effort?
So on the compression side, give us a call. That's how you do it. Yes.
That's one reason that I'm here.
Yes, so please give us a call. And once again, it depends on your particular technology. We've talked to some people where they've got great technology, but if you look at the compression ratio that they were shooting for, it's not up at that Z-level level 9 point of view, or it's not got this throughput. On the other hand, we have a variety of applications, and there are some areas where the special sauce that your company has might apply to some of our users, and because we have the FPGA in the platform, that would be one way of doing an integration. Another way is to have, if we evaluate your technology and we say, hey, moving forward, we think that this would be a great thing to incorporate, then we would also be interested in talking with you.
On the compression, I would like to take it offline. And seriously, I think that I'm hitting a very low latency and very high throughput, but that's not the goal of this question. The question is more like, say, if I want to develop a prototype, or I want to use, so I saw some reference to open source, but let's say I'm a relatively small company, I want to develop a prototype using an FPGA or using an ASIC, probably an FPGA, and using it on your system. I'm not sure I understand, I would say, even where to start, except looking at the internet.
So our current focus is really on all the FPGA work that we've been doing has really been internal development, both for our internal customers like Bing or our external customers like Azure ML. If you're interested in kind of bringing your own code, please come talk with us.
Okay.
Yeah.
Thank you.
Thanks.
Yes, about that FPGA number approximation, you mentioned about that floating point, Microsoft floating point, 8-bit through 11-bit representations, right? Yeah. And but I don't see those variable integer fixed point, maybe 8-bit to 11-bit or even 3-bit to 11-bit. Can you share some kind of your thoughts or some practice about that very flexible number representation? And people are talking about, of course, binary number representations, right? So in terms of weights.
So I'm not sure if I understand your question. You're saying that in the slide it said between 8 and 11 bits.
Yeah, floating point.
Yeah, for floating point.
So how about other representations, fixed point, and even 1-bit binary representations? Do you have support all such representation?
So this talk is really a snapshot at 2018. There's been a huge amount of work internally about what data types should be. I'm not at I can't speak to that. One thing though that in earlier work that we talked actually was presented at Hot Chips I think in 2017. We actually showed the progression. We started with 16-bit integer, and we went down to 8-bit integer, then we went to 9-bit float, and then 8-bit float. So I think that was the progression. And fundamentally, we've through each one of these successive steps, at least for our internal workloads that are important to us, we found that we can actually shrink the number of bits.
Then can user of that Azure, can he or she select any number of bits? Is it from their application code? Can you select it?
So the models that, running on FPGA, the models that are available in FPGA right now, they're fixed. So you would go and specify this is the particular model I'm running, and that would come with a certain bit type. I don't know what the future work is, but that's my understanding of what it is right now.
Hello, I'm Yao from Xilinx, and actually this is really a good idea, to kind of overcome the memory bottleneck, memory bandwidth bottleneck by distributing a lot of the distributing across FPGAs. But the question is that when you distributing the work across FPGAs, is there going to have a bottleneck through the interconnections? So could you comment on this and have more details on how do you overcome if there's any kind of bottleneck coming?
Yeah, so we're moving. So first of all, I'm not the expert. The expert was unfortunately unable to attend today. So I'm going to give you my understanding of the answer, but you should probably check with him. But fundamentally, we're moving the activations or partially computed activations rather than the weights. So we're moving order n data rather than the order n squared data. So at least the models that we've been running up until now, it's been working very well.
Hi, Alan Cantle, Molex. Just a question just around the earlier one, around the floating point numbers. Obviously, I think I heard you say you don't use the DSPs at all because they're optimized for IEEE float, and you implemented them all in the fabric. Just looking forward in a generic sense, do you see the potential to re-architect the DSP block to be much more adaptable to different types, shrinking down to smaller bit widths and exponents, etc.?
So I can't, obviously if FPGA vendors are open to re-architecting their DSPs, that would be something that would be potentially very useful. But I didn't say that we weren't using the DSPs at all. I was just saying we weren't using the 32-bit floating point on the DSPs. So the DSPs consist of more capabilities, and exactly how we do that right now is still secret. We haven't exposed that.
Hi, my name is Arad from SUNY Binghamton in upstate New York. And my question is regarding, you mentioned power is a big concern, like even 10, 20 watts can make a big difference. And I was wondering if you're working with the thermal team to develop new solutions, and if FPGAs and other ASICs that you're developing use a lot of power, and thermal is a big issue or not.
Yeah, so we definitely, the thermal teams are definitely working on this. They're looking at different ways to cool, to keep the temperatures down, to keep all of the power as low as possible. And if this is something that you're working and researching, I'm happy to put you in touch with people who are looking at those kinds of solutions.
Hi, Jeff Smith, Citadel. I had a question about the compression product and the comparative results between the ASIC and FPGA numbers. For the compression specifically?
So the three solutions that were shown there were XP8, which is less compression ratio and greater throughput.
Okay.
And so that's why that was that lower compression number. The FPGA implementation of what we call XP9 is hash table based, and they have a limit on how much they can hold for their table.
the algorithms on slide 31 were not apples to apples. One was LZ something,
Right.
and one was...
Right.
Okay.
Now, what we ended up with in our ASIC was actually a systolic array. So you find all of the matches. And so it's a bit expensive, but as you can see, you get a better compression ratio, and there's no way that that type of an approach would work on a FPGA. It would be many FPGAs.
Understood. And one question about the interface from your accelerator to the outside world. Do you guys support peer-to-peer
Yes, we do.
flows? Okay.
Yeah.
And is the interface from like a higher level more stream-based or block-based, or how do clients of your accelerator actually push things to you to compress generally?
Our front-end interface is based on NVMe. So we've adapted the command. We redid the command structure because we're sending data out and getting it back. And we put in what we need to do to tell our accelerator which paths to take. So, you can do compression without encryption. You can do this kind of encryption or that kind of. All of those things come in the command, and it's all based on the NVMe model.
Okay, thank you very much.
Hi, I'm Vasant Ramabhadran from Cadence. This is for the FPGA presentation. For the DNN and arbitrarily spreading it out to multiple FPGAs to use the SRAMs, like the previous questioner, this introduces a functional partitioning problem, right? Because any arbitrary neural network, you will have to partition. So do you have the software, any arbitrary large neural network, you will spread it out? And then a follow-on question to that is, at some point, you're going to use numerous FPGAs versus probably a traditional GPU. So you're going to have a different power equation. So how do you handle these problems?
Yeah, so in terms of tooling, there is quite a bit of tooling that's been developed to help us partition a larger model across these smaller, blocks that are being the smaller matrix vector blocks. So that's something that is internal, that we have the tooling to do that. In terms of what was the second question again?
The second question is, at some point, the number of FPGAs, the trade-off for power or other metrics with the GPU is going to be skewed towards the GPU, right? So it looks like you're locked into one kind of an FPGA solution for this Brainwave, right?
Well, so if you look at the performance that we showed, that was actually the performance we were getting is actually on one FPGA. So right now we're considerably faster than a GPU. When you start per FPGA, and this is assuming that we're going to scale across multiple FPGAs. So fundamentally, we should maintain that same power, energy efficiency even as we go bigger, because you're going to need to use multiple GPUs as well.
So the spreading to multiple FPGAs to take advantage of the local SRAMs does not cause a reduction in the cost. Is it? It's like your cost for number of FPGAs is going to go up because there's a limited number of SRAMs that you can leverage on an FPGA.
There's a limited number of SRAMs, and there's also a limited number of SRAM in a GPU as well. So I guess what I'm saying is, if we look at it on a per-chip by per-chip basis, our FPGA implementation for the models that we're running and the batch size of one that we're interested in is actually more efficient than a GPU. So if you want to go and as we scale up our FPGAs in order to accommodate a bigger model, one thing that I need to point out is we generally need that additional performance as well.
Okay.
Right. So I think what you're asking is if I've got a single model and I've just got to go and the amount of throughput I need is going to be low, right? I don't really need that much throughput. At some point, I need to increase the number of FPGAs to the point where a GPU it crosses over the GPU, where a GPU becomes more beneficial. Okay. Yeah, it's just because we're in cloud, the scale is large enough that we basically need that throughput all the time.
Yeah, and then to the first part of your presentation, you had generally I've seen this presentation about AES and encryption being accelerated on the FPGA fabric, right? But have you, for a general purpose acceleration, like any kind of compute that runs on your cloud, do you have any solution to accelerate arbitrary compute, or is it going to be like manually identifying blocks like compression or some fintech application, and someone is going to hard code these kind of applications with an IP on the FPGA?
Right now, everything we've been public about is hand-coded in Verilog and System Verilog, or we've been using some high-level synthesis as well, but fundamentally we've been focused on hand coding. We don't have an automatic way to take an application, push the button, and out pops an accelerator for it, RTL for it, and in addition to the appropriate software interaction with that RTL implemented on the FPGA. So we don't have a full tool path to do that.
Okay, got it. Thank you.
Yep, thanks.
I'm Vigyan Singhal from OSCE. My question is for Sue about alpha particles. I know Derek talked about this once in a million instance hardware bugs that we see. But now that you build these systems, how often do you actually see alpha particle bugs? And what actually happens when it's just a single bit flip or?
I'm at the end where we're preventing them rather than observing them. And so if you say, what rate do we see? Part of the problem is if you look at this million machines or 2 million machines that are running and you say, well, there was some problem, and saying what the problem is actually a whole area in itself and trying to track it down. And so that's one reason why it's really important to get something like the fit rate really, really low, because tracking these things down and figuring out what was that error that happened on 1 in a million machines a day is maddening.
So it could have been alpha particle, could have been something else.
It could be something else. It could be, you know, what I wanted was to say, all right, you think you've got this failure out there. You think it's Corsica. And I say, well, let's look at, did you pass the CRC in? Do you think it's a fit rate? Do you think this? And that we could be able to say, not just, oh, look, yes, it is us because we have the analysis, but it's equally important to be able to say it isn't us, and this is why, so that the resources can be directed where the problem is instead of trying to figure out where the problem is.
Sounds good.
Colin Lysid from Micron. The Corsica ASIC doesn't have a DRAM interface, so is all the memory on board in SRAM? And how much is it, and is it scalable?
Because we use the systolic array, it's mostly flip-flops. There are several blocks, like if you're doing decompression and you have a 64K search window, which we do, then you have blocks of 64 kilobytes of memory for each of those decompression pipelines. And then that would exist in both the 4 decompression pipelines and the 4 compression pipelines where we're doing the decompression after the compression. There are various other blocks of memory. The biggest block of memory is for the ARM processors. I think it's 4 megabytes. Might be 2 megabytes, but that's the biggest block.
Thank you.
Hi, I'm Akhilesh from Global Foundries, and I had a question regarding, so in one of your slides, you mentioned the weight spinning on the hardware microservices where you talked about the on-chip scratchpad. So I had a question about the kind of memories you've been using in it, and if, so let's say for SRAM memories, is there any kind of research or optimization going into high bandwidth SRAMs or a pseudo 2-port TDM based? And would you shed some light on any specific bandwidth requirements for that kind of memories as such?
So the memories we're talking about are on the FPGA. And so fundamentally, you know, a large FPGA these days of order 10,000 memories. In the Intel FPGAs we use, they're 40 bits wide. They can theoretically clock up to gigahertz. We don't clock that fast. But you know, let's say you can clock them at 500 megahertz. There's a considerable amount of bandwidth. Fundamentally, it's on the order of 100, you know, high tens to 100 terabytes per second of bandwidth. We can only get that kind of bandwidth if it's sitting on the die right next to the compute units that, you know, are going to be consuming them. So we haven't really been looking at researching external memories in any way. In terms of what gets put on the FPGA, that's really what the FPGA vendors are willing to put on, and obviously we talk very closely with them.
Right, if there's no more questions, let's take Susan and Derek again. So we now have an hour break, and then we're going to get back together for the last tutorial this morning. So in the first couple of tutorials, we got some infrastructure background about how to think about acceleration, and I was going to focus much more on machine learning applications. So the next tutorial is about cloud TPUs and their co-design between software and hardware. The two presenters are from Google, Clifford Chiou, who is an ASIC engineer. He has been working on TPU projects as the very first one, and he was the lead in the chip for TPU v3, and he's going to talk a little bit about this in this tutorial. And the second presenter is Brennan Saeta, who is a software engineer who was the lead for the cloud TPUs, and he's currently working on Swift for TensorFlow.
Hey, hi, my name is Cliff. Brendan is over there, and we're here to present a tutorial on how to do co-design for an architecture and infrastructure in the cloud. So before jumping in, let's start with just what is co-design, or how do we define co-design. It's leveraging expertise across disciplines and stakeholders for optimal results. So I myself am an ASIC designer. So I could just design the ASIC all by myself, but instead we co-design. So I work with folks like Brennan to do the software infrastructure. I work with people in Google Brain and DeepMind to understand what kinds of machine learning applications are coming down the pipeline. I work with the Google data center folks to understand what kinds of power, delivery, space, actual deployment concerns they have in order to create an optimal design for the TPU. Let's first start with why bother? As many people in here are familiar with, there's something called Moore's Law. It had allowed us to kind of I'll just create my ASIC, I'll create it again by myself, and I'll create it again by myself, all by just increasing my technology node or using a better technology node, and I'll hand it off to someone like Brennan, and I'll be like, hey, look, this one's double the speed. And Brennan will be like, sweet. And we were good to go. The current reality, of course, is that Moore's Law is ending, and we cannot simply rely on technology node improvements in order to create better products. So we have to actually start to, as many of the prior presenters have noted, we start to have to look at ways to make our solution a little more tailored for the actual application at hand. So I'm talking with, our application goes all the way from the data center up to machine learning research, out to the actual customers who are going to be using our services. And we talk with all groups, data center, machine learning research, software infrastructure, compilers, in order to understand what that workload all is, and so we can optimize for it and tailor our ASIC for that application. That's co-design. So my half of the presentation is about co-design for the TPU architecture. First, I'll just quickly mention that there was the original TPU V1, which we announced in Google I/O of 2016. It was an inference-only TPU, and we revealed this architecture in an ISCA paper in 2017. It's not available in the cloud, so I'm just quickly breezing through that as a little historical point. If you are interested in the architecture for it, then you can look at the ISCA paper, which was largely written by Cliff Young, who I think is in the audience somewhere here. And I also borrowed a lot of his slides, too, so thanks a lot for that. Yeah, so the meat of my presentation is the cloud TPU. How did we do co-design for the cloud TPU? The cloud TPU V2 is announced in Google I/O 2017, and we can start by jumping into the board. The board, as you can see, has 4 parts on it, and it's optimized for both inference and training workloads. 180 teraflops of computation, 64 gigabytes of HBM, 2,400 gigabytes per second of memory bandwidth across the board. How did we arrive at this final board design? We co-designed. We talked with the machine learning researchers over in Brain to understand the upcoming computational requirements for cutting-edge models that they were researching and wanting to train. We work with our systems and boards folks. How are we going to be able to, how much power can we deliver reliably? How much can we actually fit into this thing? We need to be able to put it into something that could fit into a rack. The data center, we're talking with them about cooling the whole data center, cooling the racks and the trays. These things need to be buildable, deployable. We need to be able to actually wire them all up and put them all in a reliable fashion, especially since we're building them at scale. We need to get data in and out of the actual board. So for this, we connected to a host using a PCIe Gen 3 connection with 32 lanes. Even this requires co-design. Again, we're talking with our machine learning research buddies. What kinds of input and output data feed rates are we needing for latest models? Again, systems folks, okay? How much PCIe bandwidth can I actually lay out and feed into each particular TPU? The data center. We need to be able to wire these up, connect them up. You got to connect it from host to the board. PCIe can be finicky at times, so serviceability is a requirement. Needed to be accessible for servicing. All of these things are taken into account when we arrived at what type of connection to use for our board. Now, let's dive a little bit into the actual chip architecture itself. As you can see here, we've got 2 cores, and each core has connection to an 8 GB stack of HBM memory. There's also an interconnect that allows the cores to talk to other cores off the chip, and even though I didn't draw it, there's an interconnect between the cores. So let's dive a little bit into the cores themselves. How did we arrive at, what do we have here? We've got a Cray-style supercomputer, a classic Cray-style supercomputer, where we've got our scalar unit, mostly for low latency control, vector unit, which is our kind of high bandwidth mathematical compute engine, and we've added a matrix unit, which is essentially a large systolic array of mathematics specialized for machine learning training workloads. Within each core, we've got 22.5 teraflops of computation. Again, 2 cores per chip, 4 chips per board. Most of it is in Bfloat32, but not all of it, and I'll talk a little bit more about that soon enough. How do we arrive at this? Again, co-design is involved. We look at our machine learning research friends. What types of mathematics are you actually trying to accelerate? Talk with software, compiler folks. What kind of flexibility and programmability are we going to need? What aspects of the operations of mathematics from machine learning research are best implemented through software and a compiler, and which are best implemented in the hardware directly? We also look at data center folks. They provide input for what kinds of performance metrics, metrics for thermal monitoring, power monitoring. We need to build these into our architecture, and all of that comes together to help build the core. Let's jump into the actual matrix unit itself a little bit. As I mentioned, it's a 128 by 128 systolic array. It uses a Bfloat32, standard IEEE Bfloat32 for accumulation, but we use a Bfloat16 for multiplies, which some in the audience may be familiar with, but I'll talk more about it in a bit as well. So how do we do this systolic array? How does it work? I think most of the audience is quite familiar with how a systolic array works, so I'll be quick about this. We load our, so if we want to, here I've drawn sort of a 3 by 3 systolic array instead of 128 by 128 for simplification. We want to do a dot product of a 3 by 3 matrix with 3 different 3-element vectors which is a very standard type of computation you're going to do in your neural network models, which Brendan will talk a little bit more about. So data flows down, products are calculated. As the products calculate, they shift to the right and accumulate. the first accumulation pops out from the top row, and this is your first element from the first 3-element vector. Things keep popping out, and across here, it's kind of gone off the screen, but you've got your first full 3-element vector of y. And here you got your second and your third. This allows for very high throughput for matrix multiplications, and it kind of flows through and looks nice and pretty, very cool. But why else does it matter? We didn't make it just to look pretty. The truth is it matters because of energy efficiency, because of power, because of thermal. From Mark Horowitz's ISSCC 2014 keynote, Computing's Energy Problem and What We Can Do About It. Just a quick shout out to Professor Horowitz. I was his research intern in the summer of 2000 with him and Bennett Wilburn. I don't know if they remember me. I'm not sure if I was very useful, but I hope things are going well. Anyways, where was I? Okay, so right. We would like to think that the actual amount of energy, thermal, that's needed in order to do the mathematics are all just right in the compute unit itself. But the truth is, it is not. Many of us are familiar with this concept. In order to actually do the computation, we have to fetch instruction from an instruction memory, interpret it. We need to send computation over to send the actual data into the compute unit, which requires fetching it from register, cache, wherever you're getting it. Control to tell the compute unit, hey, you're doing an add, as opposed to whatever, a multiply or floor operation or whatever you want to do. Most of the energy nowadays is actually from all of these controls. The add itself is relatively little. What you want to do is amortize that cost. So a matrix unit, a systolic array, is very efficient at doing that. As we do a matrix computation and send data through the matrix, we really are only doing one big instruction, and for each input data, we only read it once, and the controls, basically one big control that just kind of flows right through, and the whole thing just kind of flows all the data right through, and you get to amortize this cost for 16,000 operations through your entire, through the matrix unit. Leads to a lot of energy efficiency, and that is what allows us to get the bulk of our computation, such high throughput computation in the TPU. So how do we come up with this design? Again, co-design is very involved. We need input from machine learning research and from software compilers in order to know what kinds of bandwidth do you want versus what kind of latency. How do we make that proper trade-off? If it were left up to just hardware designers by ourselves, we might have made a humongous matrix unit and our latency would have gone through the roof. Software, we need proper controllability in the matrix unit. It needs to have, how can you shift in your weight tiles, and how can you control like batch widths, et cetera, batch sizes. Finally, systems teams is also providing our input on thermal limitations, power limitations. You can't just build this whole thing and just say, hey, cool it. We need to know what they're able to feasibly do, and then we have to take those limitations into account in our design. Okay, so now talk a little bit about numerics. Many people in this audience are familiar with machine learning, but I'll still go over this. In 2011, for inference workloads, it was Senior, Mao, and Van Hook wrote a paper that showed that full Bfloat32 precision was not actually necessary in order to do inference workloads. You can get by with a lot less. We took advantage of that actually in the TPU V1, which I had mentioned, that was only used for inference workloads. But eventually when we're moving on to the cloud TPUs, we are supporting training workloads, and we wanted to know, okay, maybe Float32, maybe int 8 is not sufficient for training workloads, but is full Float32 necessary? So we did our own research, and we found that, yes, you do need some Float32, but you don't need it everywhere. Again, many of us are familiar with this, but to set the stage, I'll quickly go over. Our IEEE Float32, you've got your 23 bits of mantissa, your 8 bits of exponent, which essentially are like your shift for the mantissa, allows you to express your dynamic range, very small, very large numbers. Bfloat16 is IEEE Bfloat16. You've got 10 mantissa bits, 5 exponent bits. Research that was done using Bfloat16 showed that this did not work efficiently for training workloads. You run into what is called the disappearing gradient problem. It's not able to express numbers small enough before it just makes them 0. And you run into a problem with that. So this concept in mind, the Brain team, Google Brain team, began researching another format. What if, simple concept, we keep all 8 exponent bits from Float32, because we want to have the same dynamic range and avoid the disappearing gradient. However, we just chop off a bunch of mantissa bits instead. The idea here is we've already shown that, at least for inference workloads, all these mantissa bits are not actually needed. We only needed 8. So that concept, we did a bunch of research and came up with that, yes, indeed, that works. You can do your training without loss scaling using a Bfloat16 format throughout a large portion of your training workload. This is a great example of co-design again. So machine learning research, again, came up with the idea of Bfloat16 and carried it through, did simulations, and determined where Bfloat16 could be used or not without loss scaling. Of course, it was a boon for us on the ASIC because smaller mantissa means greatly reduced power. The fact that it's half the bits, Bfloat16 is half the bits of Float32, means essentially double the memory bandwidth, double the memory storage. And of course, we took input from compiler, software team, about what other behaviors we want in this format, and they were very happy that we were able to make it support the same exact inf and NAND behavior as standard IEEE formats. So all of that essentially was in the Cloud TPU v2. The Cloud TPU v3 was announced in Google I/O of 2018. And let's dive in a little bit to what we did in there. So here we are, again, we take a look at the board. Once again, we have 4 parts. And it looks roughly similar to the Cloud TPU v2 board, except we added a nice feature. We created these colorful rope handles for us to carry it around the data center very easily. It was a nice boon for easy installation. Even better, these rope handles were also tubes for liquid cooling. So we could do liquid cooling. Very cool. So if we look inside the chip architecture, it's, at first glance, it looks roughly the same, but there are some key differences. The HBM memory stack has doubled in capacity, and we've also doubled the number of matrix units in the chip. Again, how do we arrive at this? Co-design. The liquid cooling, I'll start with the machine learning research. Once again, we get the latest computational requirements from the machine learning research group. They had started to need even more computational requirements from us, so we try to provide it. They keep on asking for more compute. I'm waiting still for the day they ask for less. Systems. The liquid cooling itself needed to be provided, but we needed to know how much could it cool, and how could we deploy it in the data center, what are the implications for that on the chip itself. Data center, of course, you need to deploy the liquid cooling, the chillers, wire them all up, and make everything work. New networking requirements were also introduced. So co-design was involved in the architecture for the entire product, from top to bottom. OK, so we've got compute. We talked about memory. One more thing we can talk about is the custom interconnect. The idea behind interconnect is we want to be able to scale up the system. First, a little bit about our custom interconnect itself. We connected things up in a 2D torus network topology. So it's kind of like a donut or like an inner tube. The custom protocol was specialized for this work case. So we were able to lower a lot of our overheads relative to other protocols, like Rocky and InfiniBand. The fact that our protocol worked the way it did allowed us to do certain kinds of algorithms in the network, such as in-network reduction. And we integrated the router right into the TPU chip, which allowed us to connect the chips directly to each other and build and scale up the system. Now, so how did we scale the system up? So I've already shown a picture of the board. This is one board, and this is the entire supercomputing pod for the cloud TPU v2. We've got, in aggregate here, 11.5 petaflops, 4 terabytes of HBM, and again, is connected in a 2D torus topology. With this humongous system, we are able to work on a single workload all at once. TPU v3, the same number of boards as the TPU v2 pod is highlighted here. We zoom out and show the whole TPU v3 pod. We've got a truly monstrous system. Over 100 petaflops of computation is available in this supercomputer, and 32 terabytes of HBM memory. The thing is, it's big. Again, coming up with the whole pod and the whole interconnect and scaling it up is co-design. Size and scope of the models and how we can lower them onto the systems is involved. So we needed to talk with machine learning research. What kinds of experiments and things are they trying to do? How can we lower them into the machines? Of course, a huge system like this needs to be put out into the data center. So we are working very closely with the data center team. What kinds of cooling, space, and network provisioning? You need a lot to deploy a thing like this, and power as well. Those limitations are all taken into account when we scale up the system. How big can we scale it? Software, programmability for parallelism infrastructure. The idea here is you've got these all these boards that can work together, but herding them all and getting them to all work together, sync up coherently is a very hard problem. As hardware designers, we were thinking about how we could actually do that. It was a difficult problem to solve, so we kind of hemmed and hawed. We were unsure what to do. And finally, we threw our hands up and said, we need someone smarter than us to figure this out. And so we talked to someone like Brennan.
Thanks, Cliff. Fortunately, I didn't have to be that much smarter than Cliff, because that was
still some.
That was not possible. But what's really important is perspective, right? The saying is that the right perspective is worth 50 IQ points, and I need those extra 50 IQ points. When you're working at scale, as we've heard earlier today, you have to think about failure. And cloud TPUs are no exception. We found that as we were trying to solve for failure, we could actually also solve for usability issues as well. So behind me is an example way of slicing and dicing up a second-generation cloud TPU pod. There's a huge number of workloads that absolutely want the biggest possible accelerator they can get, and they use the entire TPU pod as one single device. But if there's a failure, or if you're just getting started and you're not sure you want to scale up to that big of a machine, you're debugging, iterating, you can scale all the way down to a single device or what we call a quarter pod. Those are the A or the green blocks. Sorry, those are 1/16 of a pod. You got your quarter pods, those are the B ones in blue. Your half pods, C, and the full pod, D. And of course, we're designing this for cloud customers, and naturally you can request whatever portion or slice of a cloud TPU pod, 2nd generation or 3rd generation, that you'd like. So we've talked a lot about the hardware in the system. This is co-design. We need to match what we're building with the workload. So behind me is a graphical representation of Inception v3. This is an image classification model, right? Is it a cat, a dog, a truck? Hot dog, not hot dog. Image classification. And each of these boxes is what's called a layer. So the orange ones, there's a bunch of them. These are your convolution layers, right? You're sliding a tile, doing a little matrix multiplication all throughout the image. But you've got a bunch of other things as well. You've got pooling operations in blue and green, just regular concatenations of tensors in red, and a bunch of other things, including fully connected or dense layers, especially right at the end. And what happens as you go through this network, you take an input image. This is 299 by 299 pixels. Of course, you've got 3 channels, right? Red, green, blue. So you're taking this 299 by 299 by 3 tensor, and you end up converting it right before the top of the final part, sort of the output head, into an 8 by 8 by 2048 3-dimensional tensor. And so this is exactly what the machine learning model looks like, or at least this is a perspective, right, on what the machine learning model looks like. And let's see how this actually maps down to the hardware. As we've heard, machine learning is often just matrix multiplications, right? So there's convolutions, the dense layers, these are just matrix multiplication. LSTMs also just sort of look like matrix multiplication from the perspective of a hardware engineer. These run on the matrix unit. High flops, super intense, super important, used pervasively throughout these algorithms. But there's a whole bunch of other stuff that's going on as well, right? You've got a bunch of element-wise operations that run on the vector units of the chips. These are your nonlinearities, your activations, dropout pooling, et cetera. And actually, I sort of lied a little bit earlier. Those orange boxes, yeah, they've got the convolution, but they also have that activation. And so what's really neat is the way that we've designed our chips. It allows us to run that convolution part on the matrix unit and in parallel run the activations in a streaming fashion on the vector unit, exposing additional levels of parallelism that wouldn't be available without really careful co-design. In order to make this all actually work effectively, we've got our scalar unit, our scalar core. And this is for flow control, managing computing addresses, and a bunch of other operations like that. And it's only when all 3 of these come together that you have a sum that's greater than or union that's greater than the sum of the parts. And so what happens when you actually put this into practice is you stamp out a copy of that machine learning model on every single core across the entire TPU pod, and you run the forwards and backwards pass as you compute the gradients, the derivatives of the network in order to update the weights. You do it on every single core in parallel, and we leverage the custom interconnect that Cliff was talking about just a few minutes ago in order to achieve linear performance scaling from a single device up to a whole TPU pod. And we really are leveraging that custom protocol, custom interconnect for both low latency and high bandwidth. But actually, even more importantly, is extremely low jitter. This is what allows us to train synchronous gradient descent, where every core is operating in lockstep together. This has benefits both in the quality of the machine learning algorithms and the weights that are produced from this training regime, but it also means we're able to very, very efficiently utilize the hardware. So this is a result of co-designing everything from the algorithms, the training regimes, to the hardware, the software, and beyond. This is a tutorial, so it'd be a shame if we didn't at least show a little bit of code. So what does this actually look like in practice? We've found at Google putting machine learning models into production that it's extremely useful to decompose your system, your problem, into a couple different parts. And this is reified in what's called the estimator API that's part of TensorFlow. One of the hallmarks of the estimator API is it encourages you, sort of forces you, to split your program up into two functions. You've got your model function. This constructs that beautiful picture of Inception v3 that I showed you a moment ago. All the layers and how the images and labels, the inputs, flow through to the optimizer and return the result. And separate to that, you've got your input function. This is the thing that's sucking in data over the network or from storage, doing what's called augmentation, doing a little bit of randomization in order to ensure that your network trains on general images and not just the specific images in your training set. You hand these two functions to the estimator API, and the estimator API handles fault tolerance and running this system for you. And what we did with TPUs is, again, we've co-designed all these abstractions together so that you have now the TPU estimator. You provide the same model function and input function to the TPU estimator, and it's able to run. The model function runs on the TPU. It gets compiled through a compiler called XLA that we'll talk about a little bit later. And the input function is no less important, and it runs on all the hosts attached to the TPU cluster. Both of these end up scaling perfectly horizontally with 0 code changes. And this has been a huge boon to researchers and those who are actually trying to take advantage of this awesome amount of compute. TPU pods are remarkably cheap, but they're still not something you want to shove under your desk and leave idle 95% of the time. And so when you're developing or debugging your machine learning model, you can work on just a single device. But when you're ready to get the answer, train a model for realsies at scale, crank that dial up to 11, you just get your answers that much faster, no code changes. This has been absolutely incredible to unlocking huge areas of research and production. Again, this is all based on code design. We've been designing every layer of the stack, from those high-level Python software APIs, through the compilers, the runtime, the input pipelines. Everything is designed to be perfectly scalable across all these different configurations. But if you're actually solving the problem end-to-end, we actually need to take an even larger perspective. When you're training on these modern accelerators, be it TPUs or even modern GPUs, they're so fast that often dedicated SSDs can't even keep up. And so if you really actually want to solve people's problems, you need to include the storage system as well. Now, fortunately, Google has a long history of operating high-performance storage systems at scale, and it's been amazing to be able to collaborate with these folks. And what we've designed is we have everything scale out perfectly horizontally, and we're able to leverage cheap spinning Rust disks and SSDs into a sophisticated storage product that is incredibly cost-effective without sacrificing performance. In fact, we've found that some early cloud TPU customers, they found that just the I/O costs on alternate cloud platforms were more expensive than the entire cloud TPU solution, including storage, bandwidth, training, and beyond. And this is really what's absolutely necessary if you want to deliver both high performance and rock-bottom costs. What happens with cloud TPUs, of course, everything scales out horizontally across the hosts and the TPU devices. You program the system from one Python script that runs out of band. It's completely, fully parallel. In general, you're able to horizontally scale everything. And this works extremely well in practice. How have we gotten here? Well, there's a ton of choices that you have to make as you're trying to build a system like this. How much bandwidth do you actually need to provide to each host? How much bandwidth do you need to provide through different layers of the cloud storage stack? What even do you want to be using as your storage media? These are not obvious choices, and it's only through co-design, as we try and figure out what are the representative workloads and the performance of the chips, that we can figure out how to appropriately size the rest of the picture. This has worked extremely well in practice for us. Of course, we found that there's no one-size-fits-all solution. There are a lot of supervised learning tasks where you're just given a bunch of data and you have to learn a function based on that data. And cloud storage is unbelievably good for that. But there are a bunch of other things that we want to do with machine learning that doesn't look quite like that. For example, training AlphaGo 0. You don't have a bunch of pre-trained or of Go games that you're learning from. You're actually learning on the fly. So as a result, we've built 3 total ways to stream data into your cloud TPU pod, horizontally scalable with extremely high performance. We have many ways that you can DOS your TPU pod with data. And there are different, valid, and important workloads that leverage each of these different trade-offs. So let's take a look at the results. Now, before I go into this, I want to take a moment and acknowledge the folks at NVIDIA do a huge amount of work, and they do it extremely well. A lot of the early results in deep learning were built on NVIDIA GPUs. And I want to, again, really acknowledge they've been at this for over a decade, and they've done an amazing amount of work. But let's talk a little bit about what this is. So MLPerf is an industry consortium that are putting together a benchmark, right? Benchmarks drive progress and innovation as long as they're appropriately representative. And version 0.6 recently concluded a few months ago. There are a number of different sort of workloads: ResNet, SSD, Mascar CNN, GNMT, and Transformer. And we're extremely pleased with how we've been able to do in just really, under 2.5, 3 short years with our TPU platform. We've been able to truly show that with appropriate code design and figuring out how to really work effectively across all layers of the stack, we're able to achieve amazing results that TPUs are the fastest way to do certain kinds of workloads on the planet. And these are really important, commercially valuable workloads. Now, to be clear, we certainly still have our work cut out for us, and we know the space is moving very fast. But again, this is the results of code design showing that TPUs are really amazing at this important workload. Now, in order to achieve these kinds of results, we've been working really hard. And we've gotten a few lessons, hard-won lessons, that I'd like to share with you today about how you can take advantage, how you can build a system like this. The accelerators are really important to get right. And on-device execution is, at this point, it really has to be optimized by a compiler for the kinds of flexibility. If you're in the design space where you need to balance flexibility with performance, you really need a very effective compiler in order to effectively take advantage of the hardware, in order to really generate code that is in mechanical sympathy with physics. Some of the most important things is you need to leverage the size of the MXU, the 128 by 128. But also you need to think very carefully about how you're laying your data out in RAM, in both DRAM and other storage systems. And XLA is a novel compiler that takes a totally different approach to how this all needs to work. And it's able to do whole program optimizations to compute what is the optimal layout of data at every point in your program. And this is so necessary in order to achieve high performance on these TPU accelerators. Of course, XLA has built-in support for this trivial data parallel scale-out, leveraging the interconnect and other software abstractions that it's able to compile through. But of course, there's a lot more advanced parallelism possible, sharding a model efficiently across multiple TPU cores in order to leverage additional parallelism inherent within machine learning workloads. But no less important than on-device execution is, of course, the input pipeline, how you're feeding data into the TPU core. And actually, in practice, the input pipelines is where we see most of our performance problems. Because if you take a system and you take the bottleneck component and make it 10 times faster, you often don't get a system that's 10 times faster. You get a system that's 1.5 times faster, or maybe 2 times faster, because something else immediately becomes that bottleneck. And this is exactly what we've seen here. And this is going to be even more of a challenge as we have faster and faster accelerators, right? CPUs are not getting that much faster, or it's not getting faster very quickly. Whereas these accelerators, we're seeing huge improvements over and over and over again. So what are our tips for how to optimize the input pipelines? Absolutely make sure you're working effectively within your storage system, your network, and your CPU. Large parallel streaming reads are necessary. In addition, there's inherent latency in accessing memory and storage that's far away. you need to use software pipelining to hide that in order to ensure that your accelerator is always fed with data and not starved waiting for data to come over the network or be pre-processed by the CPU. But finally, there's actually a bunch of tricks that you get to play in this space, right? You can trade off between storage and bandwidth and compute as you're trying to optimize your input pipeline. Let me make this a little bit more concrete. If you're doing a lot of very expensive data augmentation, doing randomization and whatnot on the CPU, and that becomes your bottleneck, well, you can use, in a scale-out fashion, hundreds of machines to do this pre-processing and store the pre-processed images or your other training data ahead of time, trading off compute that's on the critical path with data storage. Of course, in practice, you also probably want to compress your data to save on both storage capacity and network bandwidth as you're feeding the data across the network. And so you then are trading off storage capacity and bandwidth with CPU. You've got to do that decompression on the CPU on the critical path. But these are the kinds of tricks that you get to play, and they're very interesting, and there's a lot of opportunities to do better here in this space. But how do you actually figure out how to tune your systems? You have to profile. And this is the last and perhaps most important tip that I can give. Yes, we absolutely should focus on that hero code, the beautiful, machine learning model that you show to users and say, voila, here's how it works. But this is just the tip of the iceberg. There's so much software that has to happen underneath. And in order to actually make that software work effectively, in order to debug your models, in order to solve the performance issues, you need tooling. And this is one area that I think is consistently underinvested, and one that has been a huge boon for us because we have had an awesome tools team that has built out awesome profiling tools. And so I encourage you all to check it out at that link there. You can use them for yourself on cloud TPUs today. So we've been throwing a lot of information at you. Fundamentally, given the nature of the industry as it is today, we believe that we're going to see a lot more specialization. In order to make appropriate choices in those designs, we have to co-design. This is just necessary to the end of Moore's law. It's hard. It means you've got to talk to people that don't necessarily speak your lingo, but it's absolutely worth it. You need to leverage all areas of expertise in order to actually build a system that solves people's problems. And as we've been hearing all morning, you need to architect your infrastructure for usability and scale, especially for cloud, but if you're doing specialization, you need to be operating at scale in order to justify it. And so this is another area that is absolutely important to think about as you're building systems. Make sure they're usable and scalable, monitorable, and beyond. So for cloud TPUs, we already co-design a huge number of aspects of the system. But there's one area that moves even more slowly than hardware. And that's, of course, compilers. But there's one area that goes even slower than compilers. And that's programming languages. And so that's one of the most exciting projects that I'm involved with today, and that is the Swift for TensorFlow project, where we're able to co-design everything, the programming language for what we see as where we need to be going for machine learning, acceleration, and beyond. Most importantly, the project is open source, and we have open design meetings so that everyone can come in and participate. And we'd love for all of you to join in as well. You can join the Google group, swift@tensorflow.org, and get all the details. With that, thank you very much for your time this morning. Questions?
So again, Dan, from Identify, it is well known that the coefficient that you use in convolution in machine learning have a lot of redundancy. You can compress them at the floating point level. So you improved your floating point, but I'm quite confident that you can compress them losslessly at the floating point level. Then you can use redundancy when you do the convolution, etc. There is research on it. Did you consider it in your systems?
Yes. That is all I can say.
Okay.
Sorry. Yes, we consider redundancy and optimization at basically every single level.
I'm talking about compression of the floating points.
Yes.
Yes. Okay.
Question over there.
Yeah. Mariama from Wichita. Thanks for a nice talk. I have a question about your decision to support only the Bfloat in the multiplier of the MXU. And by limiting the multiplication with the Bfloat only, I assume that some of the neural networks meant for the FP32 does not work as it is. You need a certain modification. So I'd like to know what kind of interaction between the researchers and the ASIC designer to make such a decision.
Yeah, I can speak a little bit to that. There are software methods that are available to provide flexibility to deal with a situation like that. It's about all I can say.
Well, I'll add one additional thing. In practice, we've found that Bfloat16 is a drop-in replacement for Float32 for training neural networks, and we've benchmarked this across a large variety of neural networks. And that's why it ends up working really effectively compared to Float16, which requires changes to the model in order to do what's called loss scaling. Now, we're getting a lot better at that, and there's been a lot of interesting research because, of course, we need to be able to do IEEE Float16 as well, but in practice, Bfloat16 at the input to the multipliers results in no performance degradation, no changes to the effectiveness of the models. It's just a drop-in replacement for IEEE for all the workloads we've been looking at.
Okay, got it. Thank you.
David Cantor from MLPerf. Thanks for the talk. It's great. And the shout out to MLPerf.
Yeah.
So one question I have for you is about sort of the co-design and algorithms you're looking at. You talked a lot about things that are clearly optimized for dense matrices and convolutions. Do you have any architectural support for sparse matrices, embeddings, and other things of that nature? Because certainly, we all know that Google really cares about a few problems that are sparse in nature.
Yeah, I can say that we're very aware of what you just said, and we are working on things like that. But I can't say any more than that.
Yeah, we have to smile coyly and nod. Sorry.
You can get drinks later.
Excellent.
Hi, Ani Vaidya from NVIDIA. It was mentioned on one of your slides that TPUs are optimized for both inference and training. So could you speak to what architectural features do you have that help optimize for inference, in particular other data type support beyond Bfloat?
Let's see. We do support int8 and integer operations in some of the vector units. But as I mentioned, the matrix unit is Float32 and Bfloat16. There are also a lot of the optimization is not at the numerics level, as you mentioned. They are at the system and board level. So, for example, sizing of the unit, power supply for the units, those are all taken into account when we're also optimizing for both training and inference workloads.
Yeah, so to add maybe a bit more color, Cliff is absolutely right. We are absolutely thinking of this as a systems problem, and so ensuring that we have no hiccup when the first time we use a model for inference, that we have any additional latency, making sure that we can efficiently switch out between multiple different models for multi-tenancy is sort of another example of some of the things we've been doing, really optimizing the system as a whole. And in practice, the numerics, exactly as Cliff said, we want those to be the same. There's actually a lot of advantages to that. And so it's really thinking about the problem as a whole beyond just sort of the core of the chip that we're really making optimizations for the inference side.
Thanks.
Hi, Helen Lurie from Lyft. You mentioned jitter. What's your method of time synchronization between chips inside of a pod?
The network uses a push model, and there are essentially synchronization signals that are sent out. The fact that the network is, I'm trying to figure out in my head how much I should say here, but it's it's a physical network as opposed to a virtualized network that allows us to optimize in some ways what we are doing and give better guarantees on what the tail latencies and jitter will be.
Cool. Thank you.
Michael Shea, UC Berkeley Extension. I have a question because first thing, it's an excellent talk about the technology and also even more excellent talk on the process of getting the technology put together and make them work. So the next question is on people. Would you mind giving some advice to the young engineering minds coming out of the pipeline of engineering school, what they should prepare themselves for the mentality of joining a large team, building the ecosystem as you have described so far?
I can give my opinions. I think more so than in the past, a more generic background and an ability to be more of a generalist is becoming valuable in order to do co-design across different kinds of expertises. In order to optimize things, you need to have some general skills to see where opportunities lie, where opportunities for innovation are. I also think that extends beyond just hardware, also all the way up to software as well. I also think that it's valuable to be at a place, Google is one of them, but not the only, where you have access or the ability to co-design. Whereas in certain other places, if you are isolated or you're only working on a portion of the problem and don't have access to, say a Google Brain or something, then the amount of co-design and optimization you can make will be limited. So that would be another thing to keep in mind when you're looking at what to do for your career.
Awesome. I would add maybe a couple things.
Please.
From a technical standpoint, Cliff, I think is 100% on it. I'm actually going to go look at sort of the fuzzier side. Number one is I think we absolutely always need to be learning and learning new things. Technology has always been moving fast, but I think it's only going to be moving even faster. And so honing the skills of being able to read academic papers and work across disciplines and just figure out how to keep teaching yourself things, I think is going to be the most important skill that everyone should be thinking about and optimizing for. But the final thing I'll say, and this is what I think is maybe even the most important, is we have to be working together. And so figuring out and learning how to communicate, most importantly, how to be nice to each other. This is just like, it's really valuable in my experience, and how to be humble and work effectively together. This is really how we're all going to succeed in making these breakthroughs and making these connections that are too difficult from disparate areas to fit in one person's head.
Awesome. Thank you very much.
Peter Chung, my question would be, ultimate question would be, what is that cloud TPU version 4 will look like? But then before going there, so one of the questions I had was that one of the chart that shows the linear increase of performance up to 60 TPU devices.
64.
Was that the limitation of your just experimentation? What, because of the network, TPU core speed, or beyond whatever that is, and then how that will lead into the next generation of TPU device?
So I'll take the easy question. So we only went up to 64 because that slide's old, and that was the size of our V2 pods. Our V3 pods are much larger and exhibit the same performance, but yeah, I didn't make an updated slide. So that's the easy question.
Actually, the other question is even easier, in my opinion. There is nothing announced about anything related to any TPU v4 at all.
Jim Ting. So could you give us some insight to how to think about co-design in the inference side beyond the obvious suspects?
I can say a few things about that. In fact, I'm speaking some from experience from the TPU v1. Maybe a thing to watch out for as an ASIC developer is to not over-constrain your solution. Compiler folks know how to do a lot of smart tricks. If you are able to provide primitives that compilers can take advantage of, that our software people can take advantage of, that provides a lot more flexibility to solve a much larger range of problems than if you think as an ASIC developer and you're like, oh, I'm just going to completely solve this entire thing with this one massive state machine. As an ASIC developer, you're kind of a little tempted to do that, but it doesn't leverage the abilities of our software stack and our programmers, our compilers. And then as inevitably technology moves along, the things you need to do change. Sometimes they change before your chip is even deployed out into the field. Then don't pay attention to what things the software and programmability needs are, and allow software to solve problems too. Don't just solve the entire problem all in hardware. That'd be one solid example. Brendan, I don't know if you have any more.
No, I got nothing to add.
Yeah, my name is Bhaskar from Facebook. Thanks for sharing the necessity and the advantage of co-designing these complex systems. So my question is on, yes, we need to talk with the multidisciplinary specialist skills, but talking or discussing is not enough. Something like modeling need to be done before we exploring and putting something in the hardware. So what kind of modeling you guys did and come up with this optimal solution across the board?
There are a lot of aspects of the system that need modeling. The storage, the compute, the data throughputs. I don't know. I wouldn't say that there was one. Maybe you're asking if we had like one uniform strategy for modeling, or
the different like virtual platforms or models to simulate before we decide what is the optimum hardware solution, and also software hardware interactions.
So I think I can sort of speak to this generally. We did not have the same exact modeling routine for every aspect of the system. But as a general rule, we would start with something very quick and dirty, like to try to at least sanity check some of the concepts. So something like a spreadsheet works well for that. Then you can move on to something like more like a Python model in order to explore the space in more depth and more robustly. And you could even, if you start to narrow down on something, you could start to try to model hardware costs and things like power a little bit more. So, I think I'm saying this is a little bit common sense. You start quick and dirty. As you start to narrow down some of the winning ideas, you explore those winning ideas in more depth in general.
To add to that, iteration speed, we heard from the Amazon folks earlier today. I can't underline that enough. Being able to iterate is absolutely necessary. There are a bunch of things that you can simulate, and you should absolutely build simulators, and you should model with spreadsheets and not code, as Cliff was saying, which is absolutely what you should be doing. But iteration speed is one of the most important ways that you can do it, and that's why we have been releasing new generations of chips very, very regularly, even though we have to be slightly coy sometimes.
Thank you.
Hi, good morning. My name is Sunbo. Thanks for a wonderful presentation. We're all very impressed by how far TPU has progressed in the past 3 generations, even though it started off from a very high bar. I was wondering, we saw a lot of innovation from the past 3 generations of TPU in terms of going from supporting integer to a floating point, adding high bandwidth memory, as well as a system level and application level of innovation. But one thing that seems to have stayed constant is the size of the systolic array, which is 128 by 128, which seemed to be the same for the past, for all TPUs, if I'm correct. So I was wondering if you can comment on that design choice over there, And also, does it mean that going into the future, you will envision putting more cores on a chip instead of making the systolic array larger? That would be the way to go to scale for a similar system.
Yeah, I can talk a little bit about that. The systolic array size was co-designed from the beginning with machine learning research and with the compiler folks. And we arrived at something that was providing a good balance in general across. There are many kinds of workloads and many kinds of models. There's no way to have one single systolic array size that works for every single model. But we really narrowed down pretty well that 128 by 128 seemed to hit the sweet spot and support a large swath of models very effectively. By the time you've arrived at that, machine learning research, a lot of things have changed, but that has not so much, at least not that we've noticed. Then the other aspect, of course, is once a lot of your software stack has been optimized for the latencies and bandwidths of a 128 by 128, things kind of continue along in that direction, both research and software. So it would take considerable effort to change the size of that systolic array. And at this point in time, I see no reason why, there's no known reason I'm aware of to do that.
Yeah, so in TPU v1, actually just one minor correction, the systolic array was 256 by 256. So we did shrink it down for TPU v2. But then, yes, for TPU v3, we very intentionally chose to add a second systolic array instead of changing the size of the first systolic array.
Yeah.
Hi. Actually, my question was, sorry, go ahead.
Just one more question.
Yeah, sorry.
So my question was mostly extension of what he asked previously. From TPU v3 to TPU v1 to v2, you went from 256 to 128. Is there a learning you want to share for that particular change in the architecture?
Probably the sort of the same thing I said earlier, which was TPU v1 was quick, and we as the ASIC developers didn't do as much co-design for TPU v1. We really began looking harder at co-design in TPU v2. So TPU v1, us as the ASIC engineers engineered what we thought would be best, but did not leverage a lot of the abilities of the compiler stack. And also, we did not gather all of the requirements. And so you can imagine that at 256-sized MXU, your latency will be affected by something like that. So things like this are taken into account. And so that was a learning. Basically, we figured out that the size of 256 by 256 was not the optimal point.
Was that only latency or the utilization as well?
Those both would come into play, yeah.
Okay. So is there a data that we could look at where how the utilization scales from V1 to V2 going from?
That, I myself am unaware of any public data like that.
You can create your own workloads and profile them using the profiling tools on the cloud TPUs today. So we published some utilization numbers in the ISCA paper, and then for TPU v2, we have the profiling tools available, so you can put together your own models and see how effective they are. And of course, this also works with TPU v3.
Okay. I have one more research question for the ML research group.
Keep the last person there to ask the last question, and
we'll be around.
Yeah, you can come bug us afterwards.
We'd love to continue the conversation.
Yeah, I think you mentioned that there's support for in-network reductions. And I'm trying to connect the dots. Like one thing that was also mentioned is that there is an integrated switch on the TPU. Is it that switch that supports this in the torus topology where the reductions are done?
I'm not sure I can comment too much on that, but I can say that earlier I mentioned that the network was not virtualized. So you can leverage the physical dimensions of the network topology much more readily. And that allows you to do a lot of algorithms that if it were all virtualized and things were sent, you don't actually know where, then you would not be able to do something like that.
Can I ask a quick follow-up? there was a, there are 2 cores on each TPU, and at least in the picture, you show that the memory is sort of split between the 2. So what affected that choice? Like, why did you decide to split up the total memory available on the chip between the 2 cores?
I think from the point of view of software, it was easiest to see each core. We did not want software to be visible, to pay too much attention to what was on a chip. We wanted software to pay attention to what was on a core. So we put 2 cores on a chip for other reasons like physical design and power, et cetera. But from the software point of view, we wanted each core to look the same. So you do not want to have 2 cores, but then they happen to share a 32 gigabyte stack of HBM, and then you have to go to another chip, and now you have to pay attention now to what's on a core and what's on a chip, as opposed to all cores are the same.
All right, let's thank Cliff and Bren again.